My dear JEE warriors, welcome to the next class of your 12th standard JEE physics, and that's your Gauss's law. And after completing electrostatics, I hope you have done that lecture. If you have not done that yet, please check it out in the live tab or just go to the Jungle Book. You will be able to see it, my dear students. So we have done the part one, which is electrostatic field, what is potential, what is a dipole, how does a dipole behave in a field, what is the field and potential due to dipole, and all those stuff in this particular lecture. And today's lecture is mainly about Gauss law, how to use it, what are the applications, different geometries, and flux, solid angle, all these concepts in this particular video. Okay, so let's begin with the class, and let me also remind you, as you're watching, you can go to any lecture or any class. If you have missed it, go in the description box, click that jungle book, okay, click this particular link. Yep, it will open up everything, whatever lectures, subject wise they have been arranged, physics, maths, chemistry, the chapter name, whatever has been done, the YouTube link, you don't have to search for it anywhere. The notes are over here. The DPPs will be available very soon, very quickly. Okay, so all the things at one place for all the subjects right over here in this jungle book, which is present in the description box. Okay, so let's begin. Good evening, Dharanishwaran, Joseph, Shanu. Hello, Forever RCB. Wow, nice names. Good evening. Hello, Pritika. Hello, Manisha. Hello. Good evening. Which class? This is class 12th JEE physics class. Okay, so join in, my dear warriors. You missed the previous session. Is there any problem? Shanu, I think it will be a problem if you do not understand what is field and what is potential. So if these are the main two concepts, if you know them, you can attend it. If you don't know them, then I would advise watch that particular class before this particular class. And I want everybody to participate in the chat box for every single question. No spamming. Make sure you are participating, right? For all the questions, level 1, level 2, level 3, all kinds of questions are there. With me, your captain Shreyas. Yes, let's begin. And yep, mark your attendance by hitting that like button down there. It is also a small token of your Guru Dakshina towards me, towards the channel, because everything given to you absolutely free of cost, and that too in English. Quality content, quality teachers, everything, guys. So show that token of appreciation, because we are doing this for you and students like you who never had a chance to learn in English, right? And with the best teachers. Let's begin. Ready to roll. Very good. So what is flux? This is the primary concept of this chapter. Once you understand what is flux, we'll learn how to calculate it. Then we'll go to Gauss's law, and then we'll apply it in different geometries and also see certain properties of conductor. So flux means, basically, flux means the flow of something. So for example, if there is a river and the water is flowing in streamlines like this, the flux of the liquid, which is flowing maybe inside this particular tube, maybe there is a tube over here, and through that tube it is flowing. That flux of the tube means what is the flow of that liquid inside that tube. Okay, more lines are flowing, more water is flowing, more amount of liquid is flowing, more flux is going of that liquid. Similarly, even electric field we saw can be represented in terms of lines. So you have basically electric field lines which go like this. So imagine you have a particular area, and through that electric field lines are cutting through it. Electric field lines are basically cutting through that particular surface. So if this is electric field lines which are cutting through any area, I would say there is a flux of the electric field. I would say there is a flux of the electric field. If more number of lines cut through that particular area, I would say there is a more flux of that electric field through that same area. So that is what in general flux means. So what does this flux exactly depend on? What is the formula? Electric flux is a measure of the flow of the electric field lines given through an area like you can see over here. Okay, this is the true definition of it. In fact, the symbol of electric flux is phi. The symbol of electric flux is basically phi. It is a scalar quantity. It is a scalar quantity. It is a scalar quantity. You will see soon that why the units are going to be Newton per coulomb into meter square. All right, Newton per coulomb into meter square, or else you can also put it as voltmeter. Voltmeter. That is the unit of electric flux. Why is it so? You will understand it very, very soon. Okay, so scalar quantity, phi is the symbol of it, and this flux is directly proportional to the number of field lines intersecting the surface, intersecting intersecting the surface it is directly proportional to it. A very, very important statement. A very, very important statement. So let's see the formula now, if you have understood it till here. So let's take an slide. Okay, probably I'll just have to add out over here. Okay, let me show different orientations, and in each case let's figure out whether there is flux or whether there is no flux. Say for example, there is a surface which is like this. Then in the next case, the surface just becomes horizontal. So here what is happening is electric field is coming, going like this. Electric field is coming, going like this. Electric field is going, coming like this. Electric field is going, coming like this. In this case, those electric field lines are just going from the top or from the bottom, something like this. Electric field lines are going like this or going like this. Okay, just like this. So in the first scenario, do you see electric field lines are intersecting the surface? Whereas in the second scenario, no field line is passing through. It is not cutting through. It is not intersecting the surface. Hence, I would say that in the first scenario, the flux is there. In the first scenario, the flux is there. Whereas in the second scenario, the flux is just going to be a big fat zero. So one thing is clear. The electric field was same, the area was same, but what mattered was the orientation, the angle at which the surface was kept. If you choose certain angles, the flux will be more. If you choose certain angles, the flux will not be there. So flux definitely depends on the orientation. In fact, you can also see one interesting thing, that if somebody decides to orient that particular surface at an angle to the electric field, then you will see probably some of the field lines may cut through it, whereas some of the field lines might escape it from the top and bottom. Some of the field lines might cut through it, some of them might escape it, just like over here. If I change the angle, you can see these lines which are right now cutting through that red surface will not cut through it anymore, because the surface has been tilted. So these lines might just go on that particular surface without cutting through it. So hence here the flux is going to be less. Hence over here I would say flux is there, but definitely it is lesser than, if I call this as phi 1, I will say lesser than phi 1. So this flux is there, but it is lesser than phi 1. In this case, the flux is definitely going to be 0. Is that clear, my dear warriors, till this point? Yep. Everybody with me, give me a thumbs up or write down clear. Very good. Excellent. Now, just imagine one more scenario. I have a surface. Just keep it like this. Okay. And what I do is, in the first scenario, there is hardly any electric field, very weak electric field. Whereas in the next scenario, there is a very, very strong electric field which is cutting through it. There is a very, very strong electric field which is cutting through it. Here, there is a strong electric field. Here, there is a weak electric field. Weak electric field. So what we notice is, in this case, the flux 1 versus the flux 2, the flux 2 will be more than the flux 1 because more lines are cutting through it, and that is what I told you. Flux is directly proportional to the lines cutting through the surface. So more the lines, more is the flux. So yes, it also depends on the strength of the field, how strong that field is. How strong that field is. Last thing, imagine I take a surface. Imagine I take a surface which is like this versus a very big surface like this. In the first scenario, maybe, here and there, okay, some electric field lines were cutting through it. Now what happens is, because you have taken a big surface, more lines will cut through it, because now those lines which were not going through this surface, which are going from the top or from bottom, now even those lines will intersect the surface. So hence I can say over here, if I compare phi 3 versus phi 4, phi 4 is more than phi 3 because the area factor has played into this particular scenario. So from this slide, we got to know that orientation matters. Orientation matters. From this slide, we got to know orientation matters. From this slide, we got to know that your field matters. Your field matters. From this part, we got to know that even the area matters. So what if I combine all the three elements together to get that formula? So imagine you have a particular area, and I see that some amount of electric field is cutting through it, something like this. Some electric field is cutting through this, something like this. This is the electric field. The flux passing through that area, the flux passing through that particular area is is dependent on the field, the area, and the orientation. The flux depends on the field, orientation, and the area. So the formula for that flux comes out to be electric field into area into the cos of the angle made by the area vector with the field. Now remember, maybe in 11th standard, you might have studied scalars and vectors, and you might have wondered how come area is a vector quantity. Well, area can be treated like a vector quantity in the following way. If you give me any surface, let's say for example, I take this particular booklet as a surface, and what I do is I show a perpendicular to it. I hope you are able to see that. The perpendicular drawn shows the area vector. If this book size, if the surface is small, the length of this vector will be small. If I take a big book, then the area vector will also be large. That is what an area vector is, and that's how you define area as a vector quantity. So I will show over here a perpendicular to the surface. So this becomes the area vector. This is always perpendicular to the surface. Is that clearly understood? Are you able to visualize it? You show a perpendicular to the surface, bigger the area, larger is the length of that area vector. So the angle made by the area vector with the electric field right over here, this particular angle, this is your theta. This is your theta, and that theta you will put it over here. So the flux depends on the field, area, and the orientation. Now you can see field is a vector, area is a vector, and the output is a scalar with cos over there. So hence I can also put it as electric field dot area vector. Electric field dot area vector. So it's a dot product. So everything makes sense. It's a scalar quantity, right? We can even check the units over here. We can even check the units. This is Newton per coulomb. This is meter square. You can also write, instead of Newton per coulomb, you can also write it as volt per meter. Volt per meter into meter square. Meter will cancel. It will become voltmeter. So that is why the units are voltmeter. Okay, and Newton per coulomb into meter square. That meter square is for area. This is for field. So the units also make sense. So this is the true formula for writing down the electric flux. This is the true formula for writing down the electric flux. Clear, my dear warriors, till this point? Very good. Excellent. Awesome. Why cos theta, sir? Why can't it be sin theta? Well, I'll tell you what. It's a very simple analogy. See, very good question. Imagine I take any area. Imagine I take any area and this is the area vector. Imagine this is the area vector and let's say, for example, this is the direction of the field. This was theta. Imagine I take two components of the area, as in the two shadows or the projections, or along two planes, what is the area, shadow or the component or the projection. So if I split the area into two components, one component, one component will probably look something like this, and the other component in the horizontal direction, probably I'm just showing a random diagram is like this. These are the two components of that area. Are you able to visualize? Are you able to visualize it? Okay, this area has been split into two parts or two components. Great. Now recollect how our electric field was going. Our electric field was going in this particular direction. Our electric field was going in this particular direction. Think about it and tell when that electric field is going, when that electric field is going like this, when that electric field is going like this, will the red part of the area contribute in electric flux? Will the red part of that area contribute in any electric flux? No, right? Why? Because all the field lines are going above or below it. So there is no contribution by this. Whereas if you take the green part, if you take the green part, you will notice that is playing an important role in the flux because the field lines are piercing through that area. The field lines are piercing through that particular area. So understand, when I take the two components, this component was actually the a cos theta component. This was the a cos theta component, whereas this was the a sin theta component. This was the a sin theta component because even this angle was theta actually. This angle was theta. So visualize it like this. From the sidelines, it looks somewhat like this. If you see in two dimensions, it basically looks like this. Okay, so this was your A and this was your A sin theta and this was your A cos theta. If you look at it from the side, that is why we take cos theta, because I can see only the uh, A cos theta part is contributing in the flux. A sin theta is not contributing. The flux is going from top or from below it. It is not piercing through it. Is that clear now, everyone? Very good. Excellent. Awesome. 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 Adiksha, make sure you're talking in English only over here. Yep. Correcto. Very good. So that is how you get that particular formula, which is E dot A or EA cos theta. Okay. Area vector is always taken perpendicular to the surface. Electric field can be in any direction. So EA cos theta is the electric flux. But what to do if you have a curved area? What to do if you have a curved area and that to non-uniform field? Whatever formulas we saw till now was for flat surfaces. What if the area is curved? Well, the answer is simple. Say for example, I have something like a curved area over here, something like a bent shape. Try to visualize it in some 3 dimension. And even the electric field is also non-uniform. So the electric field lines are also bent themselves, something maybe like this. Okay, so the electric field lines are also very weird looking and they are non-uniform throughout that surface. What you do is as follows. This is a non-uniform field. This can be the worst possible case. This is a non-uniform field and also this is a curved area. Some of you might have already guessed it. We will split the area into small parts, small regions, something like this. Okay, we'll split the area into small parts. Maybe I'm just showing it to you as a exaggerated example. Okay, but I'm splitting it into small parts. Just visualize it like this. Are you able to visualize it? I split it into small regions. And in each region, I can think of it as a flat surface. And in that small region, field is not changing much if I take a small area. And in that part, I calculate the flux. And then I add the flux from each and every part on that curved surface. And when I add them, basically, I'm integrating it. So yes, there will be integration involved. So all you need to do, my dear students, you choose any particular area. You choose any particular area. It could be anywhere over here. Let's say, for example, I choose this particular area. I choose this particular area over here. Let me just highlight it like this. I choose this particular area over here. That will have some kind of area vector. So that will be dA. Why is it dA? Because it's a small area. In that region, there will be some electric field. Let's say I will call it as E. So that is the electric field. So the small flux. So the flux through the element, the flux through the element the flux through the element. What will that flux through the element be? It will be d phi. It will be d phi, and that will be equal to that area vector dot producted with the electric field vector. Electric field dot that small area vector. Is that clear, my dear students? Very good. So now, if I want to find the total flux, therefore, the total therefore, the total flux is nothing but the sum, the sum of the sum of all the flux through through all the elements, through all the elements. Hence, what I will write it down as, is phi is equal to integration of electric field dot your area vector So flux is integration of electric field dot the area vector, because when I have to do sum of small elements, it is nothing but integration. So that is the answer to this particular scenario. Okay, so it's the integration of it. But now I have a problem, I have a question, which many students fail to understand, or probably don't even realize when you are doing all these things. Some of you might have even wondered about it as I'm talking. Sir, okay, say for example, the electric field is going like this. The electric field is going like this. How do you know, sir, that the area vector is like this only? What is the guarantee that the area vector is like this? Because I can show another perpendicular which is in this direction. Think about it. Whenever you take a flat surface, I can show a perpendicular coming this side or coming this side. Both options are there. Are you able to see that? Both the options are there. So which one is correct? The answer is both are correct in their own way. It is just like saying, sir, is right side motion always positive, left side motion negative? Well, that depends. Depends on your sign convention. Somebody might say left side is positive, right side is negative. No issues. It's a matter of choice, matter of convention. Understand that. So you will be wondering, sir, won't the answer change? The answer is, well, magnitude won't change, only the sign will change. And I'll tell you how. In this case, when you see that the area vector is on this side, electric field is here, the field is going towards the area vector. Are you able to see that? The area vector is like this, and the field is going on the side where the area vector is. In such cases, you will see that the flux is going to be positive. The flux is going to be positive. Whereas in this scenario, you will see that the area vector is here. The area vector is here, whereas the field is going on the other side. The field is going on the other side. In such cases, the flux value is going to be negative, but the magnitude will be the same. Let me mention that the magnitude is same, but the magnitude is going to be same. So the choice of the area vector, so very, very important. So the choice of area vector, the choice of the area vector doesn't affect the magnitude of the flux, doesn't affect the magnitude of the flux, but what does it affect? It affects only the sign of the flux. It affects only the sign of the electric flux through it. Okay, very nice concept. Very, very nice concept, right? Very good. Excellent. Let's move. Let's move. Now, there is a particular surface which is called as a Gaussian surface or a closed surface versus an open surface. I will explain this to you with this particular simple example. Is everybody able to see this pouch? Is everybody able to see this particular pouch? Very good. Now, this surface, think and tell me, is this a closed surface or is it an open surface? Is it a closed surface? I can put my hand in this. Is this a closed surface or an open surface? Everybody spam the answer in the chat box. Everybody spam the answer in the chat box right away, right now. Is this a closed surface or is it an open surface? It is an open surface because I can go inside of this. There is an opening over here. There is an opening over here. You can see that. This is the opening, right? This is an open surface. Very good. Yep, it is not a closed surface. But imagine I have these two strings. I do this. I do this. Now tell me, is this an open surface or a closed surface? Now tell me, some air is trapped inside. Okay, it's like a balloon. So now is it an open surface or is it a closed surface? Now, yes, it is a closed surface. Got it? Yes. So closed surface can be of any shape and size. There is something inside which I cannot go without piercing this surface. I cannot go inside without piercing this surface. The moment I open this up like this, that's it. It's an open surface. At the moment I close this, this is now a closed surface. Very good. Excellent. So, whenever you have a closed surface, visualize this in 3 dimension. I am showing this in 2D. Then always keep this in mind. Always keep this in mind. Area vector is always chosen outside. Area vector is always chosen outside by convention. Okay, what did I say? Whenever you have a closed surface, always the area vector for a closed surface is chosen is chosen outwards is chosen outwards by convention. Very, very important, very, very important thing, which also means all the electric flux which comes outside this flux is going to be positive. All the field lines which are going to come outside will be by nature the flux wise be positive, whereas all the field lines which are entering inside that particular surface, because they are against the area vector, this flux contribution is going to be negative. This flux contribution is going to be negative. Is that clear, everyone? Won't area vectors cancel for the closed surface, Divakar? No, I'll tell you why. Because you are not integrating area vectors, you are multiplying area vector with the field vector. So, and that to the dot product. So, area vector is not just added for a closed surface, it is just multiplied also with electric field with the angle into consideration. So, this is the most important thing which you should know for a closed surface. So, a closed surface, also keep this in mind, a closed surface is also called as a Gaussian surface. As a Gaussian surface. They are synonymous. They are synonymous. Okay. Like for example, roll number 543 in this school. Okay. Maybe Pandu. So Pandu you can say or roll number 543 in this school. It's the same person you are referring to. Okay, understood? Very good. Now, if I talk about the flux through the closed surface, the flux through the flux through the closed surface, the flux through the closed surface, phi closed. The only difference is in this formula, when I'm integrating the flux through all small elements, I have to take care of everything. So I will put integration cyclic, and then I will put electric field dot your area vector. Only difference is you are using this symbol, which is called as your closed surface integral. Closed surface integral. That is the only difference for total flux through that particular closed surface. Numerically, that will also be equal to, numerically, it will also be equal to the flux which is coming out, the flux which is coming out, if you take the magnitude of it, and you also take the flux which is going in, the flux which is going in, if you take the magnitude of it, you subtract the two. Why do you subtract the two? Because this flux is positive, this flux is negative. So if you just take the magnitude, I'll have to take the difference of it. That will give me the total flux. For example, the flux coming out here was 7. The flux going inside was magnitude wise 8. Okay, or magnitude wise, let's say 3. So the total flux will be 7 plus 3. No, 7 minus 3. 7 minus 3, which is basically 4. Okay, technically this 3 is only the magnitude. Actually, the sign wise it will be minus 3. Sign wise it will be minus 3. Is that clear, my dear students? Understood till this point? Understood? Oh, clear? Oh? Okay, how flux works? Don't worry, we are going to solve a lot of questions. Don't worry, we're going to solve a lot of questions. Now, many of you are wondering, sir, what is this symbol exactly doing? How does it know what to take the limits? So I'll tell you in a very simple way. You know, uh, do you also clean your room when your mom tells you to? How many of you do that? Or you clean it on your own, you don't have to listen to anyone, you automatically do it. So maybe this is your room. Maybe this is your room. Okay? Table is there, bed is there, chair is there, something else is there. So many things are there. Okay? If your mom tells you, if your mom tells you, de-clean, de-clean is a process. Cleaning is the process. De-clean means you clean a small part of the room. So this is like your de-clean, a small part of the room. If you clean it, that is de-clean. If I put integration de-clean means you have to clean many small parts. Maybe you are cleaning this particular region in the room. Maybe you are cleaning this particular region. If you add these small tiles, you are cleaning a particular region in the room. But if your mom tells you cyclic integral declean, that means you have to clean everything. You can't leave any area. You can't leave any area. You have to clean the complete room. Complete room has to be cleaned. That is what it means. So, my dear students, same thing over here. The symbol is telling don't leave one bit also. Take the complete area. Don't leave anything. That is what it is saying. Yeah, very good. So we have a lot of good students. Adiksha saying, sir, I don't clean. So Adiksha has a auto clean process, or Adiksha has some younger brother or sister who cleans the room for her. So yes, that is the advantage of having siblings. You order your siblings to do it. Or maybe you are the sibling who is getting ordered from your elder brother or sister. है ना? Anyways, so having said this, let's start with some questions. Coming up on your screen, a small plane area, level 1 question, is rotated in a field. Which orientation of the area is the flux of the field through the area maximum? In which orientation is it 0? Very interesting question. Very interesting question. Is the small part is a big part for me? Yes, Shiva. Even cleaning that small part is a very tedious task, है ना? Anyways, when you grow old, you will start cleaning it automatically without anybody having to tell you. Surface integral, yes. So, my dear students, if my area is like this, or if it is like this, okay, wait, I'll show it to you different places, like this versus like this. In each case, let me show the electric field. Electric field is going like this. Electric field is going like this. Electric field is going like this. In this scenario, the electric field makes an angle of 0 degrees. In this case, the electric field makes an angle of 180 degrees. In this case, it is perpendicular, so it is 90 degrees made by the area vector and the field. So in this case, if you calculate the flux, it will be EA cos 0, which is just EA. Here, if you calculate the flux, it will be EA cos 180. 180's cos is negative 1, so it is minus EA. Here, if you calculate the flux, it will be EA cos 90. Obviously, cos 90 will be 0. Hence, the flux will also be a big fat 0. So now, if you compare all of them, where do you think the flux is maximum? Where do you think the flux is maximum? It is obvious that the flux is maximum over here. So this is basically your maximum flux, and the maximum flux happens when the area vector is aligned with the electric field. Where do you think the flux is minimum? Where do you think the flux is minimum, my dear warriors? Okay, a lot of you are saying 90 degrees. Well, magnitude wise, yes, but actually wise, this is where the flux is minimum. So actually, technically speaking, this is where the flux is minimum. So because it is negative, remember -2 is even lesser than 0. Okay, understand that. So negative numbers are even lesser than 0. Hence, this is where the flux is minimum when the field and the area vector are opposite to each other. I am taking into account the sign. If you don't take account the sign into consideration, yes, magnitude wise, this is the least flux which you can get. Is that clear, everyone? Okay, so when the area vector is perpendicular to the field, then the flux is 0. No flux over here. There is no flux when your area vector is basically perpendicular. When your area vector is basically perpendicular to the electric field vector. Great. Moving on to the next question. A uniform field exists in the space in the x direction. Calculate the flux of this field through a plane of square of side 10 centimeters in the YZ plane. Take the normal along the positive x-axis to be positive. Okay, let's first of all show the XYZ axis for us to begin the question. So let's say this is our x-axis, then this is our y-axis, and then this is our z-axis. Okay, let me start marking it. This is x, this is y, and this is z. How have you placed the square? In the YZ plane. That means this is the YZ plane, taking the edge as 10 centimeters and the normal in the positive x direction. Okay, so let me show the square now. So the square is placed like this. Just visualize this. It is like this, then like this, okay, and then like this. This is your square, how it has been placed, and the area vector is in the positive x direction. That means it is like this. This is how your area vector is oriented. Are you able to visualize this, my dear warriors? Are you able to visualize this? This is how your area vector is aligned. Just visualize this. Now, where is the electric field? Where is the electric field? The electric field exists in a space in the x direction. Oh, electric field is also in this direction only. Electric field is also in this direction only. So what is the angle between the field and the area vector. The angle is going to be 0. Hence, the electric flux, which is electric field dot area vector, electric field is 100, area vector, well, it will be 0.1 into 0.1, that will be the area, into cos of 0, because area of the square will be side square. It will be just basically side square. Cos 0 is 1, 100 into 0.1 into 0.1 is just 1. Hence, the answer is 1 Newton per coulomb meter square. Or you can also use voltmeter, one and the same thing. Is that absolutely clear? Everybody with me? Understanding this process? Yep, Adiksha. Yes, Divakar. The answer is 1. Correcto. Perfecto. Awesomeness. All right. All right. Great. Okay. Let's move to the next question. Let's move to the next question coming up on your screen. And I want everybody to keep answering the question's answers. You're going to learn in this process. Next question, level 2 question. Electric field is 2 by 5 E naught I cap plus 3 by 5 E naught J cap, where E naught is this flux of a field through a surface 0.4 meter square parallel to the YZ plane is. Again, let me just show the XYZ axis. Meanwhile, you keep reading the question again and again. Meanwhile, you keep reading the question again and again. Okay, this is the y-axis, this is the x-axis, and this is your z-axis, like this. So this is x, this is y, this is z, and now again, where is it? This is my area, somewhere over here, like this. Again, it's in the YZ plane only. Okay, coincidentally very similar like before. So the area vector for the same will be like this. This is how the area vector would be. But the electric field has I cap and J cap, both components. So there is one X component of the electric field, which I will call it as EX bar. There is also a Y component because J cap is also mentioned. There is also Y component. So I'll just use different color. So there is also a Y component of the electric field. Now you guys only think carefully and tell me which of these components will contribute in the flux. Which of the X and the Y component will contribute in the flux? Because you can clearly see when the area is like this, the Y component which is there, that Y component is just going without piercing. It is just going in front or behind of it. So hence there is no flux contribution because of the Y component. So completely forget it. The only contribution will come from here, which is in the X direction, Hence, the flux is only because of the EX component, and hence it will be EX into A. EX and A both are making 0 degree. So what is the X component? It is 2 by 5 times of E naught. And what is the area? Area is 0.4. 0.4. What is cos 0? It is 1. But wait a minute. E naught value is also given to you. It is given to you as 4 into 10 to the power 3. 4 into 10 to the power 3. And then just 0.4 is just over here. Is that clear, my dear warriors? Is that clear, my dear warriors? Yes, very good. So multiply these numbers and tell me what is it that you get. What is it that you get? Come on, my dear students. You can take 1 of the 10, multiply it with the decimal, it will become 4. Then 10 divided by 5 is basically 2. 1 of the 10 will remain. So 4 into 4 into 4. Come on. Yes. 64. And then 1 of the 10 is remaining. So 640. Exactly. So the answer will be nothing but 640 Newton per coulomb meter square. Newton per coulomb meter square. Exactly. Very good. Be careful, guys. 1 of the 10 divided by 5, 2 will be remaining. 1 of the 10 multiply with this decimal, 4 will come out. Right? That decimal will go away. So this 2 into this 2 is 4. 4 into 4 into 4. Right? 64. And 110 was remaining. So 640. Exactly. Sir, I can't replay the live. No, you can replay the live. There is no harm. You can definitely replay the live. Always. Okay, it gets recorded. You can watch it any number of times. Even now, while you are watching live, you can go back behind and see what was happening just some time back in case you arrived late. Okay, so that is the answer. Moving on to the next question on your screen. Here it is. An electric field exists in space. A cube of side 2 meters is placed in the space as per the figure given below. The electric flux through the cube is. Interesting thing to note is the flux, the field is a function of x coordinate, and the field is in the x direction only. There is no y direction, there is no z direction, no y, no z. The field is traveling only in this direction. So think about it. If the field is going only in this direction, out of the left side, right side, front side, back side, top side, and bottom side, which all faces will not experience only any flux? I'll just ask you one more time over here. Think about it. This is basically your top face. This is basically your bottom face. There is front, there is back, there is right face, there is left face, there is one in the front and the one behind. Out of this, which all will not take part only in the flux, and some faces will have flux through it? Think about it. Think about it. You will be able to replay Siva after the session is over. Don't worry. Sir, we can't reply or replay. What do you mean by you can't reply? Think about it. Yep. Because the field is going like this. Because the field is going like this. Think, it is piercing through this part and coming out over here. It is piercing through this part and coming out over here. This is how the field is going. So hence, there will be flux in the right side and the left side only, whereas from the top, nothing, behind, nothing, front, nothing, bottom also nothing, because the field will be parallel to the surfaces. It is not piercing through it. It is definitely not piercing through the bottom part or through the top part. You can see that very clearly, even from the front or from the back part. So the flux is there only on the left and the right hand side. So now, once I understand that, let me just shade that for you over here. This is that phase which I'm talking about, where there will be flux. There is another phase right over here, again where there will be flux. Will the flux be same? That's the next question, because here it is entering in, there it is exiting out. I feel no, because at this point the electric field value only is very different. At this point the electric field value is only very different. You can see at this point, if I calculate what is the, it's going in, right? If it is going in, it should be basically negative flux. It should be basically negative flux. So let me just put it over here like this. Over here. What do you think is the magnitude of this electric field over here? The magnitude of the electric field at this left part, will be 2 into x. X is 2 meters. So 2 meters and I cap. That is what the electric field on the left side will be. So hence it will be just nothing but 4 I cap. 4 I cap Newton per Coulomb on the left side. Similarly, if you look at it on the right side, the field will be completely different, because x coordinate has changed. So on the right side, what is the electric field? The electric field on the right side, it is 2 into x. X is now 2 plus 2. The x coordinate is 4 meters. So into 4 I cap. So basically it will become 8 I cap. So 8 I cap Newton per Coulomb. 8 I cap Newton per Coulomb. So the field only is different. You can see that. No, the answer is not zero flux. A lot of you got it wrong. Be careful, my dear warriors. So if I ask you, on the left side versus the right side, what is the flux contribution? So on the left side, first of all, realize this. The area vector is always outside. I have already told you, whenever you have a closed surface, you always take the area vector on the outer surface, on the outer part. Keep that in mind. So that is why the angle between the field and the area vector is 180, is basically 180. So here the field will be basically 4, area will be, because the side length is 2, hence the magnitude of the area will be 2 into 2, which is basically 4 meters square. So 4 into basically 2, and what is the angle? What is the angle? It is 180 cos 180. Hence the answer will be minus 8. Hence the answer will be minus 8 Newton meter square per coulomb. Is that absolutely clear, my dear warriors? Till this point? Everybody with me? Yep. Very good. Excellent. Excellent. So the field is different. So the flux magnitude will also be different. So now going to the right hand side, the flux on the right hand side, well, that is the field value, which is basically 8 multiplied by the area of this side. The area of that side is basically 4. Oh, sorry guys, I made a mistake over here. I took the area as 2. My bad. The area was 4. So sorry. The area was 4. So the area was 4. So 4 4s are 16. So this should have been 16. My bad. This should have been 16 minus 16. Okay. Then over here, you will see the area and the field are parallel to each other. So this will be cos of 0. So cos 0 is 1. 8 4s are basically 32. So 32 Newton meter square per coulomb. 32 Newton meter square per coulomb. Is that clear, everyone? Yes, Adiksha, I took that now. So now, when I ask you what is the total flux through the cube, what is the total flux in that particular cube? What will your answer be? The flux which is going out is 32. The flux which is going out is basically, sorry, the flux which is going out is basically 32, and you have to take away from it 16. Hence, what will the answer be? Hence, what will the answer be? It will be 16 Newton meter square per coulomb. That is the final answer. Okay, the answer is 16. You can see that right over there. Cool? Clear? What a lovely question, where the field only is changing as you move along the x-axis. The magnitude is changing, hence the flux was not the same, the one which was going in and the one which was coming out of it. Beautiful question. Okay, because the field was not uniform, it was a non-uniform field question. Great. Moving to the next concept, and that is your Gauss's law. That is your Gauss's law. I will explain this to you in a very, very easy manner. After this, you will never ever face difficulty. Okay? Chalo, let's do this. Let's do this. Imagine you have a positive charge and the field due to that comes out in this particular manner. The field due to that comes out in this particular manner. And I take different scenarios. And I figure out what is the flux in each of those scenarios. Say for example, I take a surface over here, which is like this, closed surface. Tell me what is the flux through that surface. Tell me what is the flux through the surface. Quickly think and tell me. Well, whatever field line is going in is the field line which is coming out. Hence, the flux through that particular surface, if I call it phi1, will be a big fat 0, because nothing is staying there. It is going in and coming out. It is going in and coming out. Yep. Very good. Now, if I ask you, is there any flux if I take this as my surface? What do you think phi 2 will be? If I take this as my surface, do you think there is any flux which is cutting through that closed surface? The answer is yes. The flux is going out, so it must be positive. So definitely there is positive flux going through it. Now, if I take another surface, let's say over here, okay, concentric like this. Think and tell me, will the flux again be positive or not? Will the flux again be positive or not through that light blue surface? Yes, because the field lines are going out. But if I calculate the amount of flux through 2 and through 3, who will be more? 2 or 3? who do you think will be more? Or do you think they will be the same? Think about it. Come on. Dharinishwaran, yes, thank you, Warrior Pandus. It will be the same. You know why? A lot of you might think, sir, more area, so more flux. Well, let me remind you, the number of lines cutting through the pink surface is exactly the same as the number of field lines cutting through the light blue surface. And the flux depends on the amount of the field lines intersecting the surface. So if the same ones are cutting through it, why should 2 be more than 3 or 3 be more than 2? In fact, both of them are going to be equal, are going to be equal. In fact, let me also tell you, if by chance I take some another surface, let's say like this, some weird looking surface like this, in this also, the flux will be exactly the same. If I call it as phi 4, it will be the same because whatever lines pierce through pink will pierce through blue. Whatever lines pierce through light blue also pierce through the dark blue. The number of lines piercing through both of them is the same. Is the same. But if I take a surface like this over here, like this over here, whatever is going in is again coming out. So there is no flux. So this one, phi, phi, oh my God, what a name, phi, phi, okay, is going to be 0 just like this one. What does this tell you? What does this tell you, my dear warriors? The total flux in a closed surface doesn't matter how the shape is, where the charge is, where you have placed the surface, as long as there is a charge inside somewhere, the flux only depends on that charge. The flux only depends on that charge. It does not depend on anything else as long as it is inside. So the total flux through a closed surface depends if there is a charge inside or not. In red one and the gray one, there was no charge inside that surface, hence no flux. If there is a charge inside the surface, doesn't matter where it is, it will be having some flux. In fact, the flux will be the same if the charge is the same. Okay, okay. Siva, flux means flow of something. Flow of water, water flux. Flow of, anything. Magnetic field, magnetic flux. Flow of electric field, electric flux. And it is defined as electric field dot area vector. Area is treated as a vector quantity by drawing a perpendicular to the area. So area vector dot the field gives you the flux. Okay. All right. Great. Now imagine I do this. Let's say, for example, there is a positive charge and then there is a negative charge. Let's do it like this. There is a positive charge and a negative charge, and I show electric field lines through it. Electric field lines like this. This is how the electric field lines will look like. Always starts from positive, ends at negative. This is how the field lines will look like. Think carefully and tell me the answer to this particular question. If I show a surface like this over here, will the flux be positive or negative? Think about it. Flux through that blue surface. Well, all the field lines are coming out of it. So coming out means positive. So hence there will be positive flux through it. If I ask you, okay, listen, tell me the flux through this particular part. Well, all the field lines are going inside. So hence the flux will basically be negative. Hence the flux will basically be negative and it is there. If you ask me, take an area somewhere over here and measure the flux. Whatever is going in is coming out. Whatever is going out has come in. Nothing new is originating or terminating. So hence the flux through the surface 3 is a big fat 0. And also you can see there is no charge inside. Now let's take another interesting area. Let's say I choose this as my closed surface. If I choose this as my closed surface, what do you think is the total flux through it? Well, you can see some lines are going out, but that same line is entering in. You can see some line is going out and coming in. Some line is going out and coming in. This line is going out and again coming back in. So whatever is going out is again coming back inside. So hence the flux through that particular surface number 4 is a big fat 0. Interesting thing to note, even in that light blue closed surface, the total charge inside was 0. There were charges. A lot of people think if there is a charge inside, flux is going to be there. Wrong. There are charges, but one is positive, one is negative of the same amount. That is why the total charge is 0. Hence, the total flux is also a big fat 0. Hence, the total flux is also a big fat 0. Yeah, the area vector is always perpendicular to the surface. Correct. From all of this, we conclude basically what could Gauss law be? We conclude what could Gauss law be? Imagine you have some charges present and you take any random surface. There could be some charges which are inside of it. Let's say I call it Q1, Q2, Q3, like that Qn. Outside charges will not matter, but still I will show it to you. Q1, Q2, Q3, Q4, like that Qn. Different number of charges. And there is electric field, and then there is electric field because of all of them. So let's say at any given point, okay, say for example, there is electric field which is going like this, like this, like this. It could be anything. So at any given point, let's say this is our electric field at that point. Now, when I say this is the electric field at that point, is it due to these Q1, Q2, Q3 small ones or the big ones or both of them? The answer is it is because of both of them. So this is the electric field. This is the electric field due to inside and outside both. Inside and outside both. Okay, so this is inside and outside both. Okay, contribute. Both are going to contribute into this field, and this is something which you have been doing even before. Due to this, there is electric field this way. This to this, there is electric field like this. Due to this, the electric field is like this. Due to this, the electric field is like this. Due to this, the electric field is like this. You are finding the net electric field. So here, that E represents the net electric field. Keep that in mind. Due to both inside and outside charges, you show the area vector at that particular point. Let's say the area vector at that point is basically dA. So what I will suggest over here is that the total electric flux is directly proportional only to the charges inside, nothing got to do with outside. We saw that over here. When you take this surface, whatever charges are here didn't matter. Whatever charges are inside only matters. Same thing over here. If I take outside surfaces here, charges are outside, the flux comes out to be 0. So there is no contribution in the flux due to outside charge. Yeah, field contribution is there. So the total electric flux is directly proportional to the total charge inside. The total charge inside. The total charge inside. This is a total electric flux through a closed surface. Through a closed surface. Through a closed surface. Now, replicating this, what is the symbol for total electric flux through a closed surface? That is phi. Okay, that is phi, and this is closed. It is proportional to the total charge inside. That means it is directly proportional to Q1 plus Q2 like that till Qn. How about getting rid of this proportionality? How about getting rid of this proportionality? So let's get rid of this proportionality. So phi closed will be nothing but q1 plus q2 like that till qn. I need to replace that proportionality with a constant. That constant I call it 1 by epsilon. That constant I call it 1 by epsilon naught, and this becomes your Gauss's law. This becomes nothing but your Gauss's law. As simple as that. Interesting thing to note is phi closed, the closed surface integral, the flux. I have already told it to you over here. I have already told it to you over here. For a closed surface, the symbolic way of writing it is closed surface integral E dot dA. Closed surface integral E dot dA, just some time back. Hence, over here, I will just say you integrate closed surface electric field at that point is basically E vector, dot product it with the area vector locally, which is a dA. That's it. This is actually your closed surface flux is equal to the inside charge, the net inside charge. So I will just put it as summation, the net charge which is there inside, the whole thing divided by epsilon naught. So this is basically your Gauss's law formula. This is basically your Gauss's law formula. Is that clear? Okay. This is exactly this one over here. I just replace this with this. That's all. This is your Gauss's law formula. Cool. Everyone? Awesome. Awesome. Okay. Okay. Cool. Guys, concentrate on the class. Dharneshwara and Adiksha. Come on. All right. Concentrate. This is Gauss's law. The total electric flux on a closed surface is summation inside charge by epsilon naught. It does not depend on the outside charges, where the inside charges are, etc. Also, the field over here is because of both inside as well as outside charges. Both of them are having contribution in that. Keep that in mind. Okay, I've just put it up over here in the form as well for all of you. Let's start with some questions. Ready for some questions? Put some fire in the chat box. I want to see some fire. Come on, no more chatting between each other's. Fire of the chat box right now. Ready? E naught means, where is E naught? Where is E naught? There is no E naught over here. E dot. This is dot product. It's not E naught. It is E dot. The dot product. This is epsilon naught. Oh, epsilon naught. That is epsilon naught, my dear warriors. That is permittivity of free space. That is your permittivity of free space. Yep. Okay, cool. Let's go. Questions coming up on your screen. First level question shown below is a distribution of charges, the flux of the electric field due to these charges on the surface S. On the surface S, some surfaces are shown. One surface here, one surface here, one surface here, another big surface here. So if you are talking about the surface number S, this is the one. This is the one. Who are the charges which are there inside? This is there inside. This is there inside. Notice how this charge is basically outside. So what did we just say? The total flux in a closed surface is the total charge which is there inside by epsilon naught. Here, what is the total charge? Q plus Q divided by epsilon naught. So this will be 2Q divided by epsilon naught. So 2Q divided by epsilon naught is answer number 2. Very good. Dharineshwaran, Adiksha, very good Divakar, very good Bhavni, very good. Proud of all of you. Moving to the next question. An electric dipole is put in the north-south direction in a sphere filled with some liquid like water. Which statement is correct? Electric flux is coming towards the sphere. Electric flux is coming out of the sphere. Electric flux is entering into the sphere and leaving the sphere are same. Water does not permit electric flux to enter into the sphere. Interesting thing. So what do we have is a dipole in a sphere filled with a liquid. So imagine this is that sphere. This is that sphere, and we have a electric dipole. So we have the positive charge over here, and we have the negative charge over here in the north-south direction, and this is being filled by water. This has been filled with water. Okay, this sphere has been filled with water. Now, water has some permittivity. It definitely permits electric field lines. So, option D is definitely wrong. It's not like electric field will not come. Definitely, there will be electric field. In fact, you will see that the electric field lines will go like this. It will go like this. This is how the electric field lines will go. This is how the electric field lines will go. You can also see whatever field lines are going out are again coming back inside. Whatever field lines are going out, they are again coming back inside. So electric flux is coming out or in? Well, wrong. Electric flux entering in and coming out are the same. This should be the most appropriate answer. Net flux is zero. Please mind that. Net flux is a big fat zero because the amount of positive flux and the negative flux is the same. The amount of positive flux, here there is positive flux, and the amount of negative flux, both of them are same. Hence the total flux will be zero. It is not coming out, not coming in totally. It is equally going in and out. Hence the answer is 3. Very good. Moving on to the next question on your screen now. If the flux which is entering in and leaving a surface is phi1 and phi2, what is the charge inside the surface? Very interesting question. I want everybody to solve this question really quickly. Come on, my dear warriors. Come on. Think about it and answer the question. Come on, my dear warriors. Replay is not available. I think I know why probably replay was not available. There is some warning which it was showing over here. Not sure why. Okay. A lot of you are saying D or A. Let's figure this out. The total flux is the charge which is inside by epsilon naught. Now think about it. Here, some flux is entering in and leaving. So flux which is entering, the flux which is entering will be negative. Flux which is entering will be negative. So this is minus phi1. The electric flux leaving is entering is negative. So this is minus phi1. The electric flux which is exiting is basically phi2. Okay. This is basically equal to Q in divided by epsilon naught. This is basically Q in divided by epsilon naught. So Q in, the Q in will be nothing but phi2 minus phi1 and take that epsilon naught on the top. So that's it. So phi2 minus phi1 into epsilon naught. Remember, entering inside is negative and exiting out is going to be positive. So that's why I have put that minus sign over here, because this is going inside and the one which is going outside is as it is anyways positive. Hence the answer will be option number A. Is that clear, my dear warriors? Yep, option number A is the correct one. Cool. Moving to the next question coming up on your screen. 4 surfaces and their charges are shown as below. Let the respective fluxes be phi1, phi2, phi3 and phi4. Flux through this phi1, through this phi2, this phi3, this phi4. Compare them. Compare them. Very, very straightforward question, my dear students. In the first case, flux 1, charge inside is 2q. So it will be 2q divided by epsilon naught. In the second case, just see the charges inside. Q, Q, Q minus Q. So actually it is Q plus Q plus Q minus Q divided by epsilon naught. It is again 2Q by epsilon naught. That is basically your phi2. That is basically your phi2. Let's go to phi3. Let us go to phi3. What is phi3? Only 2 charges are there inside. Rest others don't matter. So Q plus Q divided by epsilon naught. So again it is 2Q by epsilon naught. What about phi4? Phi4. 8 minus 2 minus 4. 8 minus 2 minus 4. What is this? The whole thing divided by epsilon naught q times. So this is again going to be 2q divided by epsilon naught. Every answer is 2q by epsilon naught. So hence the correct answer will be C for Captain Shreyas. C for Captain Shreyas. Yep. Very good. Excellent. Very nice. Moving on to the next concept, and this is the concept of solid angle. This is again useful for mainly advanced problems. Mains wise, not so important, but yeah, it might come, who knows, once or twice, few questions have been related to this particular concept, but very rare. See, whenever you have two lines and there is an arc between that line, you can measure the angle. But imagine you have something like a surface and something is covering that surface, you get an angle in 3 dimension, which is called as the solid angle. Just like over here, there is an arc, and that length of that arc is given by, you can see there is some kind of radius over here. There is some kind of radius over here. So it is r times of theta. This is your plane angle. This is basically your plane angle or angle in 2 dimension. When you have a 3 dimensional surface, when you have a 3D angle, sorry, and you have a surface like this is the surface. The angle which it subtends can't be in 2D. It has to be a 3 dimensional angle. It has to be a 3 dimensional angle. This is that angle which I'm talking about. This is that 3D angle that we are talking about. How much angle is being subtended by this surface which is shaded in yellow. So if again the radius, if again let's say the radius or the distance from the surface till here is, let's say, r, then I would say the surface area, that surface area over here is nothing but r square, into that solid angle. The solid angle can have multiple symbols. Sometimes people use phi, psi, anything. Here I'm using omega, sigma, whatever you want to use. So that is solid angle's relation with the surface area. Just like length of the arc is r times theta, the area of the surface is r squared times sigma, pi, whatever you want to use. Okay. So this is your solid angle or angle in 3D. Solid angle or basically angle in 3 dimensions. Now, let me also tell you one very interesting thing. Just like you take two lines, this is the angle between them. Imagine you open those two lines, you open that line and you bring it back over here. So if you come back till this point, the total angle is 2 pi radians, right? 2 pi radians. Same way, in solid angles, imagine you take a small area. The solid angle that you have is represented over here like this. If you take the entire surface around you, up, bottom, right, left, front, back, entire thing. So it will be like a sphere only. It will be like a complete sphere, the solid angle. Then the solid angle is 4 pi sterdian. Solid angles is measured in sterdian. Plane angles are measured in radians. Plane angles are measured in radians. This is measured in sterdians. Interesting thing to note is just like length of the arc is r theta. If I use it over here, I will see the length of the arc will basically be the circumference, and the length of the arc formula is the radius times theta. Theta is basically 2 pi. Well, that is correct. Circumference is 2 pi r. Perfectly correct. Here, if you notice, the area of the sphere, will be the total area on that surface, the total surface area, and the total surface area using this formula will be r square into that sigma, whatever symbol you want to use. So it will be r square into 4 pi, which is actually the area of the sphere, 4 pi r square. 4 pi r square. Yes, ST means sterdian. Sterdian. Okay, this is steradian. Steradian. Okay. Right. That is the unit of solid angle. Like you have radian, degree. Same way for solid angle, it is teradian. Cool? Clear? Very good. So now think and tell me, if I take a hemisphere, what is the solid angle of a hemisphere? If I take a hemisphere, what do you think is the solid angle of a hemisphere? This is a hemisphere. Come on, put it up in the chat box immediately. If you take a hemisphere, for a complete sphere, it was 4 pi radian. For a hemisphere, half the solid angle is here, half the solid angle is there. If you divide the circle into two parts, obviously it will be 2 pi steradian. 2 pi steradian. Correct? Everyone? Is that clear? Understood? So now comes the real question. What if I don't have a hemisphere, but some random, let's say, circle, and some random circle, and I know this as my R. I want to know what is the solid angle subtended. What is the solid angle subtended at the center? What is the solid angle subtended at the center? So it so happens that if you treat it like a cone, if you treat it like a cone and join a line from the center to the vertex and then happen to measure the semi-cone angle. What is theta? Theta is basically your semi-cone angle. Semi-cone angle. And this sigma is basically your solid angle. There is a relationship between them. There is a relationship between them. And that relationship is the solid angle is 2 pi into 1 minus cos alpha. 2 pi into 1 minus cos alpha. As simple as that. 2 pi into 1 minus cos alpha. So sigma is basically nothing but your 2 pi into 1 minus cos of theta, where theta is the semicone angle. This is in steradian, this theta is in radian. As simple as that. Keep this in mind. Keep this in mind. Is that okay? Everyone? Clear? Very good. Don't spam, guys. Whatever questions you have regarding something else which is not relevant to the topic which I'm teaching, put it up in the comments after the session is over. I will try to respond to it. Is that okay, Shirish Reddy? Right. Now, why is this solid angle concept also important? I'll tell you in a very simple manner. See, if I take a point charge, if I take a point charge, okay, Q, and I see how the electric field lines go, it will go front, back, down, below, everything, everywhere it will go. If I measure the total angle through which the entire flux goes, the entire solid angle, the answer is it is 4 pi steradian. For 4 pi steradian, the flux is, the electric flux is how much? Q divided by epsilon. Q divided by epsilon naught. 4 pi steradian. That means up, front, back, everywhere. It is going in all the directions. All the solid angle is covered. So the flux going is Q by epsilon naught. Now, for that same charge Q, if I take only a small part of it, if I take a small part of that entire region where the flux is going, meaning something like this, okay, the flux is only going through that particular small region, where the solid angle subtended, is this much, where the solid angle subtended is, let's say, this particular sigma. Okay, how much flux goes through that part? How much flux goes through that part can be found by unitary method. For 4 pi, it is this much. For this, how much? As simple as that. So the flux passing through that particular part, will be Q by epsilon naught is for the entire 4 pi steradian. So for that sigma steradian, how much will it be? That is the answer to this particular question. That is the answer to this particular question. Hence, phi will be Q divided by 4 pi epsilon naught into the solid angle which is there. Into the solid angle which is there. Again, a very, very important looking formula. This is your flux. This is the charge. This is your normal constants. This is your solid angle. As simple as that. Is that clear? Everyone with me? Everybody with me? Cool. How to find that sigma? I have already given to you over here using this formula. You can definitely find it out. Okay, I have already given you that particular formula. So there was a question probably asked. Let's see if there is that question somewhere. There is this question which was asked in JEE Advanced 2017. A point charge Q is placed just outside, just at the apex of an imaginary hemispherical surface of radius r. Which of the following statements are correct? So multiple options can be correct. That's why it's a level 3 question. Let's see how do we do this. Read the options carefully. Okay. Now, some options are very easy to solve. Let's see which are those options. The component of the electric field normal to the flat surface, the component of the electric field normal to the flat surface is constant over the surface. Well, I mean, what they are saying is this is that flat surface. Here, the electric field, which is the component of the electric field normal to the flat surface. This is that EY component of that total electric field. This they are saying this is constant. How can it be constant, guys? First of all, the distance is changing, the angle is changing, everything is changing. So 100% it is not going to be constant because this angle will change and even this distance is changing. Even this distance is changing. So this distance is changing, this angle is changing. So electric field is also going to have different magnitudes. As you go far away, field will reduce. The component will also become small. So 100% that is not the answer. So I'll just duplicate this slide because I'm going to need it. So this is 100% wrong. This is 100% wrong. The circumference of the flat surface is equipotential. Circumference of the flat surface. So if you see this is the flat surface, let me from this charge join a line to any point on the circumference. This distance is going to be a constant. This distance is going to be a constant. So if you measure the voltage at all these points, it will be a constant. Correct? It will be just KQ divided by R. KQ divided by that particular distance. So hence, no matter where you go, even here or even here, no matter where you go, my dear warriors, everywhere you will see the distance is same. So all these points are equipotential. So hence the circumference of the flat surface is equipotential. So D option is correct. Hence D option is definitely correct. Now total flux through the curved and the flat surface is Q by epsilon. Total flux through the curved and the flat surface, how can it be Q by epsilon naught? Think about it logically, my dear warriors. I mean, this answer is definitely wrong because curved and the flat will become a closed surface, and the flux in a closed surface is the charge inside by epsilon naught. How much charge is there inside this hemisphere? This Q is outside, nothing is there inside. So this is basically zero. So Q by epsilon naught, 100% wrong. 100% wrong, guys. This is wrong. Are you able to see that? It is not Q by epsilon naught. Q is there outside. So it is 0 by epsilon naught, and hence the total flux is 0. Yep. So A and C are wrong. D is correct as of now. So let me mark all the wrong options over here. As of now, only D option is correct. We need to figure out the A option, which seems to be the toughest one. Let's see the sign first. The electric flux is negative. Electric flux is negative through the curved surface. If this is a closed surface, obviously whatever field lines go through the curved surface will be negative because you're going inside. Hence, this negative sign is justified. If I did not see the negative sign, if this was just like this, I would have crossed this out because the flux won't be positive, it will be negative. It's going in, hence magnitude wise, sorry, sign wise it is correct. So negative sign, negative because the flux is going inside the hemisphere. It is going inside the hemisphere. Perfectly fine. What about the magnitude? What about the magnitude? So for that, I realize one interesting thing. Observe this. This base is not just the base of the hemisphere, but also the base of an imaginary cone. Just imagine, just imagine a cone now. Just imagine a cone over here, like this. Just visualize this. Imaginary cone. And now you can see electric flux. Now you can see electric flux passing through it. Now you can see electric flux passing through it like this. Now you can see electric flux passing through it like this. See, are you able to visualize it? Electric flux is piercing through that particular base of the cone. So for doing this, I will obviously need this formula. It is Q by 4 pi epsilon naught into sigma, but I need sigma. That sigma is given by 2 pi 1 minus cos theta, where theta is the semicone angle. So over here, what is the semicone angle? The semicone angle is this one. The semicone angle is this one. So this is theta. And you can see the base is also going to be r. If this is r, this is r, how much is theta going to be? How much is theta going to be? It is going to be 45 degrees, which is basically pi by 4 radians. Agree with this? This is a isosceles right angle triangle. Height is also r, base is also radius. So what is our solid angle going to be? What is our solid angle going to be? What is our solid angle going to be? Sigma. So that sigma, remember, it was 2 pi into 1 minus cos theta. So 2 pi is as it is 1 minus cos of 45 degree. What is cos of 45 degree? It is 1 by root 2. So that is basically your sigma in stadian. But that is not the question. The question is how much how much flux is going through it. How much flux is going through it. And I just showed it to you over here. The flux is measured by Q by this into sigma. Q by 4 pi epsilon naught into that sigma. Okay, so the flux passing through it will be equal to Q divided by, the Q is Q capital, by 4 pi epsilon naught into sigma, into basically sigma. So that sigma I will substitute over here, which is 2 pi into 1 minus 1 by root 2, and these things as it is, Q by 4 pi epsilon naught. 4 pi 2 pi cancels, only 2 is remaining, hence the answer will be Q by 2 into 1 minus 1 by root 2. Q by 2, sorry, epsilon naught, 1 minus 1 by root 2, which is perfectly correct magnitude wise. So this is the magnitude of the flux which we just found. Hence option A is correct. So correct answers are A and D. Correct answers are A and D. B and C are wrong. Yes, we are done. This is how you have to solve this question. Please enable DVR in stream settings. Okay. Now I understood why this was not opening. Okay. Now check if it is working. I have enabled DVR. Is this clear? Cool. Yeah, we are going to come to cube related problems in a bit. Just hold on for a second, Kanishka. Okay. Yeah. So this is how you solve this question. Next question is over here. This was asked in JEE Advanced 2022. Believe me, this is very, very straightforward. Again, you might think that we have to probably use our, these formulas to solve the question, but let's see whether we have to use it or not. A charge Q is surrounded by a closed surface of an inverted cone and a hemisphere of radius r as shown. The electric flux through the conical surfaces. Now, this question feels like, okay, you need to use the concept of solid angle, but actually, you don't have to. Sir, why the negative sign? Dhanashri, I think I just told it to you before in this slide. Because where did it go? Because the flux is going in. Because the flux is going in. Do you see that? The field lines will be going inside the surface, hence it is negative. Sign convention. Negative because inside it is, the charge is outside, it is entering inside the closed surface. Okay. Now, let me tell you over here, this problem is very straightforward because the field lines will go something like this. The field lines will go something like this. Observe this. Can you see one interesting thing? Whatever is happening on the top is happening below also. Whatever is happening on the top is happening below also. Is happening below also. Can you see that, my dear warriors? Can you see that, my warriors? So whatever flux goes on the top is also going below through the cone. So can I say the flux through the hemisphere, through the hemisphere is also the flux through the cone, is also the flux through the cone, and together they make the total flux. So hence each one of them will be half of the total flux, half of the total flux. So what is the total flux because of a charge? It is the charge divided by epsilon naught. Now over here they say it is nq by 6 epsilon naught. That means it should be 3q by 6 epsilon naught, because 3 by 6 is half. 3 by 6 is half. Hence the value of n should be nothing but the number 3. Hence the value of n should be nothing but the number 3. There is no need of solid angle concept in this particular question. There is no need. Got it, everyone? Awesome. Perfect. Okay, so this J advanced question, which looks like a level 3, actually happens to be a straightforward question. Moving on to the next one, and that is application of the Gauss's law in different ways. Sir, but what is the relation between solid angle and flux through CSA of a closed surface area of a hemisphere? Mathematically okay, but conceptually I could not understand. Relation between solid angle and the flux through any forget hemisphere, any surface you take, my dear students, this is the relationship. Flux is q by 4 pi epsilon naught sigma. Okay, for a hemisphere, what was sigma? I just told it to you over here, right? Where did it go? I gave you example. For a hemisphere, solid angle is 2 pi steradians. 2 pi steradians. So if you substitute it over here, for a hemisphere, 2 pi, 4 pi, 2 will cancel, 2 will be remaining, 2 epsilon naught. So q by 2 epsilon naught for a hemisphere. Basically, half the flux is going up, half the flux is coming down. The total flux was q by epsilon naught. So half of q by epsilon naught on the top, half of q by epsilon naught below. That is how you should look at it. Is that okay, Vishaldi? Is that understood? Clear? Okay, very good. Excellent. Let's move now to the different applications. Now these are the important things which you should know. See how to apply Gauss's law and different geometries. You might be wondering, what is the use of Gauss law? The use of Gauss law is to find the electric field. The use of Gauss law is to find the electric field due to standard geometries like wire, a point charge, or maybe a sheet, or maybe a sphere. All these things you can find the basically the electric field without even integration. Now I know you guys are thinking, what are you even saying? I thought Gauss law is just all about integration, because if you see the statement of Gauss law, there is integration in it, and you are telling me you can avoid integration. Yes, that is the irony of Gauss law. Even though you have this complex closed surface integral over here in the Gauss law formula, but when you actually use Gauss law to find the electric field, it becomes simple. It simplifies the process. In fact, most of the times you can avoid the integration. You can avoid the integration, and that makes it very simple. So let's start with simple geometries first. And here is the first geometry that we have, that is a point charge. Now point charge is very simple to explain and understand, that's why we start with it first. So let's say we have a point charge over here like this, a point charge over here like this, and I want to find out the electric field at any given point, let's say at a distance r. So let's say for example, yeah, so let's say we want to find the electric field at this particular distance r over here, at this particular distance r over here. Okay, and I know one thing, that the electric field at that particular point, the electric field at that particular point will be probably like this. So this is the electric field. I want to find out how much this electric field is. So first things first, what we are going to do, we have to apply Gauss law, right? So we have to choose a surface. How that surface should be? Closed. Now, I will choose the surface in such a manner that applying that integration will be easy. The application of that integration is easy when one of these things happen. Either the electric field is parallel to the area vector, because then cos of 0 will be 1, or the electric field is perpendicular to the area vector. Basically, cos of 90 will be 0. So either you take the field vector to be parallel to the area vector or anti-parallel, and the second aspect is either you make it perpendicular. Now we know, no matter where I go around this charge, the electric field is radially outwards. The electric field is radially outwards. It's natural now to think the surface that I will choose will either be parallel to the electric field. Well, it looks very weird. Perpendicular makes sense. I can choose a nice sphere. I can definitely choose a nice spherical surface around it. So let's basically choose a spherical surface around it. Let's basically choose a spherical surface around it. Something like this. Yes, this is my Gaussian surface. This is my Gaussian surface. And why did I take it? Because I know no matter where I go, if I show the area vector, that area vector is parallel to the electric field or it is perpendicular to the surface. Perfect. Matches. So this much part is done. Now comes the next step. Let me apply the Gauss's law. Let me apply the Gauss's law. What does Gauss's law say? Cyclic integral electric field dot area vector is nothing but total charge inside by epsilon naught. Okay. Now, if you go to any given point, no matter where you are, field and area vector are parallel to each other, so angle is 0. So it will be magnitude wise electric field into area into cos of 0 degrees is equal to inside charge. Inside this surface, there is only one single charge and that is Q. So I'll just put Q and I divide it by epsilon as it is. Cos of 0, 1. Best part is electric field, no matter where you go on the surface, because the distance is same, the electric field magnitude will be same. Hence, when something is a constant, you can definitely bring it outside the integral because it is a constant. And cos of 0 was 1. Cos of 0 was 1. So it will become E cyclic integral of area is equal to Q divided by epsilon. Now, what is this integration of area? Basically, you have to add all the areas on the sphere. Every single part of the sphere, you cover it. So it will give you the total surface area of the sphere. Oh, so this means I have to find the total surface area of the sphere, which is 4 pi r square. You complete every single area of this particular sphere, you will get basically 4 pi r square. Great. So that is basically Q divided by epsilon naught, moving things around. So it will become E is equal to 1 divided by 4 pi is there, epsilon is there, Q is on the top, R square is below, which looks exactly like KQ divided by R square. This is how you get the formula, KQ by R square. Isn't it interesting? Isn't it interesting, my dear warriors? Very good. Excellent. Yeah. So that is the electric field, and I have proved it to you. And this is how that 1 by 4 pi epsilon naught comes. A lot of you always wondered, sir, how did you know it is 4 pi? Why not 2 pi, 3 pi, 7 pi, etc.? It comes via Gauss's law, right? So using Gauss law, indirectly, I have come to Coulomb's law. So I don't need Coulomb's law anymore if I know Gauss's law. Vice versa also true. If I know Coulomb's law, I don't need Gauss's law. But Gauss's law sometimes makes the job easier. So yeah, probably Coulomb is crying in the corner once you use Gauss's law. Clear? Everyone? Till this point, good evening, anime gods. Cool. Let's move on now to the next few geometries. But before that, some questions coming up on your screen. Consider the charge configuration and the spherical Gaussian surface shown. While calculating the flux of the field over the surface, the electric field will be due to which of the charges? Electric field, when you are using in the Gauss's law, cyclic integral electric field dot area vector is inside a charge by epsilon naught. What do you think you consider in the electric field? Come on, come on. Yes, it is because of both. This is because of inside as well as outside. If you were there present even before, oops, where did it go? If you're present before, you know this. I have told it to you over here. It is because of inside as well as outside charges. This electric field is because of both of them. The flux is only because of the inside charge. Yep. Hence the answer to this question. Hence the answer to this question will be both. All the charges inside as well as outside. Not just positive, not just negative. Everything. Yes, number 3. Correct, Agent. Awesome. Moving on to the next question on your screen. A charge is placed at the center of an open end of a cylindrical vessel. This is a cylindrical vessel. Visualize this. And charge is placed at the center of that open end. At the center of that open end. Question is basically how much flux is going through the surface of the vessel. It's not that difficult if you visualize another cylindrical vessel on the top. Just imagine this part over here. Just imagine the bottom part over here like this, and our charge is present exactly over here. I just geometrically construct one more part over there. So if you show the field lines, the field lines will go like this. If you show the field lines, the field lines will go like this. How much ever flux goes below also goes on the top. How much ever flux goes on the top also goes below. In fact, the total flux by that charge will be Q by epsilon naught. In the upper part or the lower part, it is exactly half of that total flux. Upper part or the lower part, it is basically half of that total flux. It means it is half of Q by epsilon naught. So half of Q by epsilon naught, which means answer C is the correct one. So Q by 2 epsilon naught. How many of you got it? If you got it, proud of all of you. That is the correct answer. Cool. Let's go ahead to the next question coming up on your screen. There is a charge which is at a distance of a by 2 above the center of a square surface of edge A as shown in the figure. What is the flux through the square surface? This was asked in 2018. This was asked in 2018. Now, again, just like here, we constructed an imaginary cylinder. I feel over here, you might have to construct an imaginary cube, and then things will fall into place. Just construct an imaginary cube. You will understand what exactly is happening. So, showing a cube over here. This surface, which is over here, this one, this surface, okay? Let me show it over here below. This is that surface. This is that surface, okay? And that charge is at a distance of a by 2. That charge is at a distance of a by 2. Oops. That means somewhere over here at the center. Yes, this is basically your a by 2. This distance is a by 2. Imagine the cube side is a in length, a in length, a in length. This is a by 2. That means it is exactly at the center of the cube. That means cube is exactly at the center of that particular cube. Now the flux will go equally on all the sides. The flux will go equally on all the sides. Agree or disagree, my dear warriors? No matter where you go, the flux will go equally on all the sides. Like some flux will be coming this way. Some of the flux will be going right side. Some of the flux will be going towards the left side. Some of the flux will be going on the top. Some of the flux will be going below. Some of the flux will be going behind. Equally in all the directions the flux will go. So can I now say that the total flux which is coming out of the cube will be 6 times the flux coming through any one side, any one side. And what is the total flux which is going through that cube? It is nothing but Q divided by epsilon naught. That is 6 times the flux through any one side. Hence, the flux through any one of the side, take that 6 below, will be Q divided by 6 epsilon naught. It is Q divided by 6 epsilon naught, which is option number D, which is basically option number D. Understood? Yes, ID Delhi is the correct answer. Yes, Divakar. Correct. This is how you solve these cube related questions or anything like that. In fact, you might probably also see a question. Oh, we'll come to it probably. Yeah, this also is a very nice question. A cuboid of dimension 2L by 2L into L. Charge is placed at the center of the surface having area 4L square. What is the flux through the opposite surface to S given by? Interesting questions. Okay, if you understood how to solve this or even this, you will be definitely be able to solve this question, because it is just about imagining the surface, imagining where the charge is, and sometimes constructing something so that calculation becomes easy. Constructing an imaginary surface. Yes, there is scholarship, Sudarshan, for joining our offline centers. If you visit any of our offline centers, you will get the scholarship. You can check in your nearest cities. But if you are looking for online batches, already the prices are very, very low, and the kind of facilities that you get are at very minimal cost. So for online, there is no scholarship. Okay, okay, cool. So how do we solve this question? Let's imagine this surface first. Let's imagine this surface 2L into 2L into L. Okay, so 1 second. Check this out. This is basically L. This is 2L, and this is also 2L. Okay, 2L into 2L into L. This is the cuboid. It's not a cube. And a charge Q is placed on a surface of area 4L square. This is that surface which we are talking about. Okay, this is that surface which we are talking about. It is placed over here, exactly on this part. It is placed exactly on this part. So that charge is placed maybe somewhere over here. Charge is placed exactly over here. This is that charge. Okay. Now the question is the flux through the opposite surface to S. Opposite surface to S is behind it. Opposite surface to S is behind it. So let me just create a duplicate and okay. So it's exactly behind it. Just try to visualize this now. It's here. Okay, it's somewhere here. Exactly behind it. That is the question. Okay, find the flux through it. What I will do is, I will visualize another cuboid of same kind on the other side, basically in front of it. just imagine another cuboid exactly in front of it, something like this over here, something like this over here. Just try to visualize this. Just try to visualize it. Now, isn't that charge Q at the center of the cube of side? What is the side? L plus L. Just check this out. This is basically 2L of side 2L. It's now a cube, no longer a cuboid. That L you multiplied, you make two cuboids besides each other. Now it is at the center of it. So now think, for this particular blue part, whatever flux is there, the flux passing through that shaded part, it's a side of that big cube, and 6 such sides are there for the cube. So into 6 will give me the total flux of the cube, which happens to be Q by epsilon naught. Hence, the flux passing through that particular side will be Q by 6 comes below 6 epsilon naught. So where is it? Option number D. Yes, that is correct. Yes, that is correct. Is that clear, everyone? How we solve this particular question? Okay, it's a beautiful, beautiful question. I'll just showcase to you again over here. This charge was at the center of this face, and we had to find the flux through the opposite face. So I constructed one more cuboid on the side so that it now becomes a big cube with a charge at the center. And I know the total flux through the cube is Q by epsilon, and this blue part is one of the side of that big cube. Hence, I can find the answer very easily, which is Q by 6 epsilon. Clear? Okay. Okay. Yes, Gugan, let me tell you the name of the chapter. I read the comment just probably yesterday or today somebody had mentioned it. So in the Jungle Book, now you will see, if you go to the Vedantu Jungle Book, just click on this link. You have to sign up. You can see now I have segregated everything over here. I asked the team to segregate it. Physics, maths, chemistry, chapter name, YouTube link, everything. All the links present over here. So properly maintained. PDF is also there. DPPs are also going to come very soon. Just hold on for some time. Okay. So you can click on any of the PDFs. Okay. Any chapter and it will open up over here. Okay. It will open up over here. Any chapter. All the notes are present right over here in the Jungle Book. Jungle Book link is there in the description box. Fair enough. Shall we go ahead? All right. Let's move. This is done. Next question. Charges 5q and minus 2q are situated at 3a, 0, minus 5a, 0, respectively. The flux through a sphere of radius 4a having center at the origin. Let's think about it properly. Let's draw the x-axis over here. This is the y-axis. Where are the charges kept? 5q is kept at 3a, 0. 1, 2, 3. Let's say over here. This is basically a charge of 5q, and this distance is basically how much? 3a. Okay, next charge, minus 2q at minus 5. 1, 2, 3, 4, 5. Maybe over here. This is a charge of minus 2q, and this distance that you see from here to here is basically 5a. This is basically 5a distance from here to here. You take a sphere of radius 4a. You take a sphere of radius 4a. So 4a is more than this but less than this, and center it at the origin. So I think it will be something like this, I believe. Okay, so this is how it will be. So this sphere has a radius of how much? 4a. This is what it is. So the question is, what is the flux through the sphere? Well, the only inside charge, the flux through the sphere, if I calculate, which is the inside charge by epsilon. Inside charge is 5q, 2q is outside. So hence it will just be 5q by epsilon naught. 5q by epsilon naught is answer number D. So D is the correct answer to this. Thank you, Divakar. Great, Gugan. Yes, Dharneshwaran. Sir, will you cover capacitance also in this class? No NN ideas. This is only purely for Gauss law. Capacitors will be a separate chapter because, see, this is not a CBSE channel. In CBSE channels, what they do is they follow exact NCERT flow. This is a JEE channel. So we will divide the chapters as per JEE flow. So in JEE, any book you see, SC Verma, DC Pandey, capacitors is separate chapter. Okay, so that is the reason why we will treat it separately. How come minus pi is inside the circle? Minus 5a, where is minus 5a? Minus 5a is not inside the circle, it is outside. So this charge is basically outside. This is basically outside the circle. Only this plus 5q charge is inside. The distance is 3a. The distance is 3a. This is 4a. So 4a is more than 3a. This is inside. Is that okay? Adiksha, I hope this is clear. All right. So that was answer number D. So now if you have got full confidence, shall we go to the application parts? Taka tak, taka tak, taka tak. Last few things. Okay, we'll see all the geometries one by one. Everyone, ready for it? Okay, few geometries we'll see now, and then we'll take a break, and then we'll again return. Okay, few geometries before and after the break. Cool. Let's begin. Electric field due to a uniformly charged infinite wire. Infinite wire. Okay, let's see. Infinite wire, right? So how will an infinitely charged wire look like? Oops. This is an infinitely charged wire. It's having some charge maybe on it. And usually what will be given to you for that wire is something called as lambda, which is linear charge density. Linear charge density, which is how much charge is there per unit length. dq by dx or dq by dl, whatever you want to call it. Charge per unit length. The unit will always be coulomb per meters. How much coulomb of charge is there per meter? Excellent. Now, if you take a long line charge like this, which extends infinitely, very, very important that word infinite, because we are going to see finite also soon. This is an infinitely long wire. How will the electric field lines look like? Just think about it. It will be radially outwards for sure. It will be radially outwards for sure. So I think it will look something like this. One line will be going here, one line will be going here, one line will be coming here, then one line will be going here, something like this. Just try to visualize this, guys. It'll look something probably like this, right? And the same thing will continue in every plane which is parallel to this. In every plane which is like parallel to this, something like this. Just making you visualize it properly. Just see if you are able to visualize this. So you will have an electric field which is radial and perpendicular to the wire 100% it is non-uniform. It is non-uniform because the field strength is definitely changing as you go far away. They are not parallel to each other, they are radially spaced. Is that right, everyone? Now, the concept over here is to find the electric field. Like I told you, always choose a Gaussian surface which is either parallel or perpendicular to the area, to the field, sorry. You choose a Gaussian surface which is always perpendicular or parallel to the area. So the natural thought process of choosing the Gaussian surface would be to choose a cylinder, to choose a curved surface. And on that curved surface, these field lines will be definitely perpendicular. You can see they'll be perpendicular to the surface itself. So let's imagine that, and it looks something like this. I think I had put this before. Yeah. The electric field line is always perpendicular to the curved surface. The top and the bottom the field lines are, not intersecting. They are just passing through the surface like that. Okay. So I have chosen a cylinder, which is my Gaussian surface. So I've chosen a cylindrical Gaussian surface, cylindrical Gaussian surface. Perfect. And that cylinder has a radius of r. That cylinder has a radius of r and a height. You can see a height of basically L. A height of basically L. At any point on the curved surface of the cylinder, the field will be constant, and let's say the magnitude is E. On the upper and the lower part, please realize one interesting thing, that the flux will not flow through this part or even this part. There will be no flux over there. There will be no flux in these parts because the field is not piercing through that area. Only the flux is there on the curved surface area. Cool. Next important thing, you choose any area vector at any given point on that curved surface. That area vector on that curved surface will be parallel to the electric field. So if I apply Gauss's law now, which is cyclic integral electric field dot area vector is equal to inside charge by epsilon naught. This flux, I will split it into two parts. One part is the flux through the top and the bottom, plus the electric field flux through the curved surface, This is equal to Q inside by epsilon naught. I just split the flux into two parts, the flux through the curved surface plus the flux through the top and the bottom surface, which will make up the entire cylinder. Best part is this is zero because I just told you no flux will be there through the top or the bottom. So this is just a big fat zero. Whereas only through the curved part, if you see, the flux will be nothing but electric field into the area and the angle between them is zero. So cos zero. Perfect. Do you understand why cos zero? Do you understand why it is basically cos zero? Electric field and area vector, they are parallel to each other, so angle is zero. Great. Next important thing, Q inside. How much charge will be there inside in terms of the length? Just now I told you lambda is the charge per unit length. So the charge which is there inside is only this much charge. Only from here to here. How much ever charge is there only in this much part? This much is the charge inside. So this is the charge inside. That will be charge per unit length into the length. Think about it. Because lambda is charge per unit length. So the charge will be lambda into the length. So it is directly proportional to the length. So whatever is the length, accordingly, the charge will be decided. So I can just put it over here as lambda into L, and this is divided by epsilon naught. So let's see what does this turn out to be. Electric field is a constant on the curved surface. I hope you can see that electric field everywhere on the curved surface is a constant. So this will just come outside the integration. Cos of 0 is 1. So it will just become electric field integration of that area on that curved surface. Cos 0 is 1 is lambda L by epsilon naught. What is the area of the curved surface of a cylinder? It is 2 pi r into the height. So that is what it is. So lambda into L divided by epsilon naught. Now interesting thing to note is that L is there here also. It is there here also. So both the places it will just get cancelled off. So what is the value of the electric field that we are getting? Shift that 2 pi r below. So you will get electric field is equal to 1 by 2 pi epsilon naught. Lambda on the top, r below. So that is the value of the electric field. which you can also write it as 2 times of k into lambda by r, which is fine because k is 1 by 4 pi epsilon naught. 2 cancels with the 4 becomes 2 pi epsilon naught. Perfect. Nothing wrong in this. So this is the formula for the electric field. This is the formula for the electric field due to an infinitely charged wire. Okay, very good. Sir, is that the charges are present inside the cylinder or outside? They are present everywhere, Shruti. But you can see we will only consider the charges which are present inside. Excellent. Okay. Okay. Very good. Excellent. Now, via integration, you can get it for a finite wire. I will just show you how beautifully that formula is there. By putting some special values, you can come back to this formula for infinite wire. Okay, observe this very carefully now. I will just show you for a finite wire. When I say finite wire, it means it is having some start and some end. So let's say our finite wire was like this. This is our finite wire. And at some distance you are standing, maybe over here, standing. And you want to find what is the electric field at that particular point. Lambda is given to you for that particular wire. So every point charge on that wire, will give some or the other electric field. Like this point over here will give an electric field like this. This point over here, because the distance has increased, the field will be slightly less. This point over here will give even lesser field because the distance has been increased more. So the field contribution will be less. This point will give a field in probably this direction. It will be even less. This point will give a field in this direction. It will be even lesser field. Same thing will happen here also. There will be field because of this point charge over here in this direction. There will be field in this direction, but it will be even less because the distance is more. So this is how the fields will come from different charges above and below. Now, depending on whether they are symmetric or non-symmetric, there might be a Y component remaining in the net electric field. There may not be a Y component in the electric field. Do you understand it? Imagine it was completely symmetric. So the number of field lines like this and like this, number of field lines like this and like this, number of field lines like this and like this will be same. So the net field in the Y direction will be 0. But imagine in one particular direction there are more field lines. Then you will see there will be a resultant unbalance in the Y direction. There will be a resultant unbalance in the Y direction. So generally for finite wires, you may have a residual Y component. So I will just show it to you over here. So let's say, my dear warriors, we have the X component and we also have residual. Now in this case, this is more. So the Y component will be on the top. So this is the Y component. So that's it. So this is the Y component of the electric field. And similarly, we also have the X component of the electric field. Are you able to see that? Are you able to see that, my dear students? So this comes via integration and the formula is as follows. For the X component, what you need to do, very similar to this formula, very similar to this formula or even this formula, it comes out as follows. K lambda by R, you put it over here. Same thing for even the Y component, EY component, K lambda by R. You put brackets. Same thing over here also. You put brackets. What you will have to do, one more thing is, measure this angle from the top to the center, whatever this angle is there, just measure that angle till the perpendicular. Let's say I say it is alpha. Also measure how much is this angle. Also measure how much is this angle. Let's say that angle is beta. Measure these angles alpha and beta from the extreme ends till the central line or through the perpendicular line. Here, For that x component, you will just put sine of alpha plus sine of beta. For the y component, you will, instead of sine, put cos of alpha minus cos of beta. That's the only difference. For the component which is perpendicular to the wire, it is sine plus sine. For the component which is parallel to the wire, it is cos minus cos. As simple as that. Let's put this formula to a test. Let's put this formula to a test. Okay, let's put this formula for a test. Say for example, for an infinite wire, for infinitely long wire, for an infinitely long wire, if I'm standing over here, can you tell me what is the value of alpha and beta? Well, since the wire is endless, so the value of alpha and the value of beta both will be 90 degrees. Both will be basically 90 degrees. Everybody agrees with this? Wow, perfect. So what will be the x component? X component will be k lambda divided by r sine 90 plus sine 90. What is sine 90? It is 1. So it will be k lambda by r, 1 plus 1, which is 2. So it will become 2k lambda by r. Exactly what we expect it to be. Similarly, if I ask you what is the y component, it will be k lambda divided by r cos 90 minus cos 90. Anyways, cos 90 is 0, so it will just become a big fat 0. Cos 90 is 0, 0 minus 0 is 0, so it is 0, which is perfectly what we were expecting it to be. There is only x component, there is no y component. The electric field is 2k lambda by r in the horizontal direction. There is no y component here. Amazing, right? So this is how it works. This is how it works. Similarly, let's say we take another example of a semi-infinite wire, very, very important example. If you take an example of a semi-infinite wire, what is the meaning of semi-infinite wire? It means the wire is like this. This extends till infinity over here. It stops over here. It is infinite only on one side. It is half of a infinite wire. And now if you are standing at some distance, let's say r, and I want to find the electric field, there will be again now two components, one in the x direction, one in the y direction. So if I just try to find out how much is that x component first, I need to first mark the angles. This is endless. So if I join from this point to the end, this particular angle alpha will be 90 degrees. But the second end is over here only. So if you notice, these two lines coincide. So beta will be 0 degrees. Beta angle, because this point is not here. If it was here, beta will be something. But now beta will be 0 degrees. So now there will be x component also, and there will be some y component. In fact, the y component will be like this. Why is the y component below? You can understand why. Because these charges will give an electric field in this direction. So in this direction, there will be two components, one right side, one below. So what is the x component? So the x component will be k lambda divided by r sine of 90 degrees plus sine of 0 degree. Sine 90 is 1, so sine 0 is 0. So it will be just k lambda by r. It will be just k lambda divided by r. If I measure the y component for a semi-infinite wire, it will be k lambda by r into cos 90 minus cos 0. Interesting. So it will become k lambda by r. Cos 90 is 0, cos 0 is 1. So it is coming out to be minus k lambda by r. Don't get scared because you are getting the answer minus. This minus is telling you it is not in the positive direction, it is in the negative direction. But magnitude wise, the y component is equal to the magnitude of the x component. That is the most interesting part of this entire problem, which happens to be k lambda by r. The y component and the x component both come out to be the same. Is that clear? Yep. Awesome. Very good. Hello, DPP logs. Yes, I've seen this in Enthuse times Pathfinder. Very good, Divakar. Okay. Is this point clear? How to find the electric field due to either finite, semi-infinite, infinite, etc. So these formulas are very, very important. This is like the God formula. The special case of this is infinite or semi-infinite or any other thing. So if you know this, you can get this or even this or this, doesn't matter. Let's see one more geometry. Let's see one more geometry, my dear warriors. And that is your electric field due to an infinite sheet. So let me just keep it over here. So we are trying to find the electric field due to an infinite sheet. Electric field due to a large sheet. Okay, how to find this out? Let's again consider a sheet which is charged. Let's say I show a sheet like this. And there are charges on it. And what is given to me is something called as sigma, which is area charge density or basically charge per unit area. So it is like dq by dA. And the unit of that is coulomb per meter square. Coulomb per meter square. If you take one small area unit, on that, how much charge is there? That is basically sigma. If sigma is more charges are concentrated per unit area. How will the field lines look like? Obviously, you can think now, because it's a large sheet, each charge will give field in all the directions, and because there are charges everywhere on the sheet, the field lines will become parallel. The field lines will end up becoming parallel and it will look something like this. It will look something like this. So this is how the field lines will look like. And the best part is because these lines are parallel, these electric field lines are uniform. That means no matter where you go, this side, how far you go, the field strength will be constant. So you will get a uniform field on both the sides. Now, the question is, how much is the field strength? How do I calculate it? Using Gauss's law. Just like I said before, Gauss's law, if you want to apply to simplify, the calculation, always choose the area perpendicular to the field. So looking over here, it is the best to choose a cuboid-like structure, one part on this side, one part on this side, so that some charge gets enclosed inside. And then I can find the field using Gauss's law. It looks something like this. Look at it. Cuboid or cylinder, doesn't matter. So the structure should pierce through the sheet. Okay, the structure should pierce through the sheet. So this is your Gaussian surface. Okay, and it has some charge which is enclosed right over here. So the charge enclosed, is right over here. So how much is the value of the enclosed charge? Because sigma is charge per unit area, So charge will be sigma into area. So it will be nothing but sigma multiplied by that area. Let's say for example, whatever area is there over here or over here, if I call it as A, okay, this is also A. This area will also be A only. This area will also be A only. So hence that area part will be just A, and this is into sigma. So inside charge, one thing is very, very clear. It is sigma into that A, which is the base of the cylinder or the circular part of the cylinder. Till this point, I think everybody is clear. Cool. So this is our Gaussian cylinder. This is our Gaussian cylinder. So if I apply Gauss's law, which is cyclic integration of your electric field dot area vector is equal to inside charge by epsilon naught. I will now again split it into two parts. One part is those bases, that circular bases, and the second part is the curved part. Just look at the curved part, my dear warriors. Just look at that curved part over here. Just look at that curved part. Do you see that everywhere on that curved part, the electric field lines are parallel either this way or that way? So there is no flux which is passing through that curved part. For any curved part, you will see the electric field lines are parallel to it. Hence, can I say, when I break it into two parts, when I break it into two parts, I break it into two parts, there will be a zero part because of the curved surface. Because of the curved surface, because the field lines are parallel to that curved surface area. The field lines are parallel to the curved surface area. But there will be a part which will be contributing in the flux, which is the circular base, which will be the circular base. So there will be flux only because of the circular base, but there are two such circular bases, so two times of it. Two times of it, because the circular base is here also and here also, both of them are contributing in the flux. Is that right, everyone? This is equal to your Q in divided by epsilon naught. But wait a minute, Q in, we just figured it out right from there. It was nothing but sigma into A. Sigma into A. What is the flux through the circular base? Guys, it's a constant field. Don't even have to integrate. You just can write it as electric field into area. Electric field into area. And the best part is the area from here and the area from here will just cancel out. Hence, the electric field will become sigma. Oh, I forgot that epsilon naught here. Epsilon naught here. So it will just become sigma. That 2 goes below 2 epsilon naught. That is the formula. So the electric field due to a charged sheet is sigma by 2 epsilon naught. Is sigma by 2 epsilon naught. Is that clear, my dear warriors? Everyone with me? Understood? Clear? Awesome. Awesome. Perfect. So this is the formula due to a charge sheet at any distance. It is independent of the distance. It's uniform. Sigma by 2 epsilon naught. So till now, we have seen multiple geometries starting off with a point charge. If you notice, point charge, we studied this. KQ by R square, which is normal formula. We have seen this before also. Then we solved many problems on that. Then I showed you due to a wire. Then I showed you due to all special cases. And then a sheet, which is sigma by 2 epsilon naught. Now, we will study hollow sphere, solid sphere, and then some properties of conductors after the break. Okay, so let's take a break. So it's a small break time. It's 7:35. So 7:55, let's meet. Meanwhile, please like the video. Okay, please like the video and obviously share. And if you are watching it recorded, comment. Okay, if you are watching it live, at least share it. And if you have not yet subscribed, subscribe it. Okay, so I'll see you guys in a bit. Uh, Anime God will continue for maybe 1 hour more after this, 1 to 1 hour 15 minutes. So around 9 o'clock, the stream will end. Hello, hello, hello. Hello, guys. Am I audible and visible? Just let me know quickly in the chat box. Yo, your break time is over. Done with your dinner, my dear warriors. Done, done, done. Ready, fully refreshed. Come on, light up the chat box. Get in all your friends. And I see that you are interested more in the 11th standard syllabus than in the 12th standard syllabus. Is that so? Where are your 12th standard friends? Still not studying? Hello, anime god. Yep. Hi, Jaya. Hello. Ethical. Hello, Dharmeshwaran. Yo. Yep. Divakar, I just had my dinner. Yep, yep, yep. Done. So, time to begin. And let's get started. Yep. By the way, this week we would have 1D motion, right? Before this, we have already completed vectors, units, and dimensions. Even the electric field potential dipole concept was done in the first class. This is the next chapter. After this, which chapter you want me to take? Do let me know in the comments. Do you want me to take capacitance or do you want me to take ray optics from 12th point of view? Okay, do let me know. Chalo, let's begin. The last few things, electric field due to hollow sphere, then due to solid sphere, and then some properties of conductors and their problems. That's what we are going to do. So hollow sphere means obviously inside part is completely empty. So imagine we take a sphere like this. Yeah. Imagine we take a sphere like this. The charge is there only on the circumference, on the surface. That's the meaning of hollow. Okay, that is the meaning of hollow. Okay, and let's say this particular sphere has some radius r and a total charge of q Now, yeah, for solving this problem using Gauss's law, why Gauss's law? Because it is simple. I want to find out what is the field at any given point. I want to find the field inside. I want to find the field. I want to find the field inside. I want to find the field outside. So I will take two cases. I'll take a point inside and I will imagine a Gaussian surface. And because it's a sphere, it is natural to think of the Gaussian surface also to be spherical in nature. So I will also draw a very simple spherical Gaussian surface here inside. Okay. And for the outside part, I will draw a Gaussian surface like this. I'll draw a Gaussian surface like this. And let's assume you are standing at a distance of r and you want to find out the electric field here. Let's say the electric field is E. And at that particular location, if you see the area vector will also be along the electric field vector. Same thing over here inside. Again, let's say that small r is lesser than capital R. I want to find out the electric field at this particular location. And I can see that there will be an area vector like this. And maybe the electric field is like this. So both inside and outside. So first case number one, when you are inside. Case one, when you are inside. And when I say you are inside, it means small r is less than capital R. Then we will go to case number two, when you are outside. So basically R more than R. That is the second case. Now, if you take the first scenario, my dear warriors, my dear lions, if you take the first scenario when you are inside and you apply Gauss's law, remember, this is our Gaussian surface, that blue one. This is our Gaussian surface. So let's apply Gauss's law. Cyclic integral electric field dot area vector is inside charge by epsilon naught. Is that right? Okay. Now, at every given point on that sphere, electric field and area vector are parallel to each other. So it will just become electric field, area vector and cos of 0. But you know what the best part is? It is on the RHS. How much charge is there inside this particular sphere? There is nothing. There is nothing at all. Correct. Because the charge is only on the surface. It's only on the hollow sphere. Nothing is there inside. So there is a big, big zero over here. There is a big, big zero over here. Nothing is there inside. Nothing is there inside that Gaussian surface. Hence, what I will get is the electric field inside is a big fat zero no matter where you go. The electric field is zero no matter where you go. That's a very interesting thing that you are seeing over here. What happens when you apply it for outside? Let's see. Cyclic integral electric field area vector into cos of 0 is equal to q in divided by epsilon naught. Notice how the electric field is constant everywhere on the Gaussian surface because the distance is the same. So the magnitude of the field is constant. So I can just bring it outside. Cos of 0 is not 0, sorry, it is 1 because the electric field and area vector are in the same direction. So angle between them is 0. Cool. So bring that electric field outside. Cyclic integration dA is there. And what is the inside charge? If you see the blue sphere, which is our Gaussian surface, which is our Gaussian surface, inside this sphere, the entire charge of the sphere is enclosed. So hence the enclosed charge is also capital Q. So the complete charge Q is inside the imaginary Gaussian sphere. So then this will become electric field. What is this? Integration of area. It is the area of the Gaussian surface. Please mind this because this is always on the Gaussian surface. So a lot of people make a mistake and they write it as 4 pi capital R square. That is wrong. It is 4 pi small r square. It is the electric field over this area. So when I'm calculating the blue area, so it is the area of the Gaussian sphere. It is the area of the Gaussian sphere, not the actual sphere. Hence 4 pi small r square. That is equal to Q by epsilon naught. Hence the electric field outside will be 1 by 4 pi epsilon naught Q divided by r square. That is the formula, just like we got over here. Now the best part is when you look at these formulas, you realize this formula is like the field due to a point charge. So it feels as if the entire charge of the sphere is concentrated at this point and you're trying to find the field here. So when you're outside the sphere, the charge of the sphere appears to be concentrated at the center. But when you're inside, then the fields cancel and the net field becomes a big fat zero. Is that right, everyone? In fact, that is what I have also put it up in the graph form somewhere. I think I would have put it in the next slide. Yeah, so this is the combined formula. So when you are inside, it is 0. When you are outside, it is kq by r square. When you are outside, it is kq by r square. And I can just say inside a shell, the net field is 0. Inside a shell, the net field is 0. This is the first conclusion. The second conclusion is when outside, when outside, the charge on the shell, the charge on the shell appears to be concentrated at the center. Appears to be concentrated at the center. So it behaves like a point charge. So it behaves like a point charge. That is what the final conclusion will be. Great. And if you see the graph, because inside it is 0, suddenly outside it is 1 by r square. So the graph will be something like this. Inside it is 0, outside it is 1 by r square. As simple as that. So inside it is 0, that's why it is flat over here. But the moment you go outside, you can see it is like this. That means it is inversely proportional to r square. So that is how the electric field versus distance graph looks like. This is the electric field versus distance from the center. This particular point is the radius of the shell. So till this point it is 0. Suddenly when you go outside it is 1 by r square proportional. Right? Everyone with me till this point, is it clear? So the shell is one of the most important geometries, let me tell you that. And this proof is also very, very important, not just from board's point of view, but even from JEE advanced point of view. You might see so many problems where radial distribution or radial charge density or something like that is given, and you have to find this using similar laws. And this graph also has come many times. This formula is also used so many times in so many problems. Let's move on to the next part, which is the potential. Because now I know that how a charged shell behaves, inside versus outside. So I think it is very easy to figure out its potential as well. It is very easy to figure out its potential as well. So let's say this is R, this is Q. The charge is only there on the surface, mind it. The charge is only there on the surface, nowhere else. So when I am inside versus outside, I think outside is very simple. So the potential outside will be the potential due to a point charge. The potential due to a point charge. As simple as that. So you are standing somewhere here. I want to find out the potential at that particular point. The potential outside, I can think as if there is a charge concentrated here and then solve the problem. That's it. Just think as if there is a charge concentrated at the center and then solve the problem. What is the potential due to a point charge? It is KQ divided by small r. That's it. That is the potential outside. That is the potential outside when R is more than R. As simple as that. Is that clear? So this is the potential outside a shell. KQ by the distance from the center. Yep. Is hollow sphere actually a shell? Yes, Divakar. Hollow sphere shell means the same thing. Hollow sphere or shell means exactly the same thing. Next important thing is when you are inside. When you are inside, then what to do? Let's say you are somewhere over here and you want to find the potential. Now, a lot of you will think, sir, the answer will be 0 because the field is 0. Because the field is 0. Just think about it. Just because the field is 0, what does it mean? Okay, electric field inside is 0. Electric field is related to potential by this formula, minus dV by dr. Minus dV by dr, right? Electric field is dV by dr, force is du by dr, negative sign. So hence, dV inside by dr is a big fat 0. That means the potential inside is not 0. In fact, it is a constant. In fact, it is a constant. So it is constant in this region. So whatever is the potential inside will also be the potential on the surface. Will also be the potential on the surface. Now, what will be the potential on the surface? Just use this formula. Just put small r as capital R. Just put small r as capital R. So therefore, V in will be KQ. Instead of small r, you will put capital R. That's it. That is the answer. That is the answer because the potential on the surface is KQ. Instead of small r, you will put capital R. So you have substituted small r as capital R. That's it. That is the answer. Hence, the potential inside is KQ by capital R. All of them are constants. So it is uniform everywhere. It is equipotential. This point, this point, this point, this point, this point, all are having the same potentials everywhere. All of them have the same voltages everywhere. There is no voltage difference. Hence, there is no electric field. Hence, there is no electric field. Is that absolutely clear? Everybody with me? In fact, there is a graph also for potential. We'll see that as well. So very, very important. Field is 0, potential is constant. Inside, field is 0, no field, so no voltage difference. Outside, it behaves like a point charge. So whatever is the potential or the field due to a point charge, exactly that. Exactly that. So if you draw the potential graph versus distance, it looks like this. It is constant KQ by R till the surface. Once you reach the surface, it is inversely proportional to R. Once you reach the surface, outside of that, inversely proportional to the r. Is that clear? Everybody with me? Cool. So we have seen sphere completely. The derivation part, right? The inside outside part for the field, how it behaves, as well as the graphs, as well as the potentials inside outside and their graphs. Ready for solid sphere now? Ready for solid sphere, my dear warriors? Okay. Now, solid sphere means the charge is there. That means the charge is there everywhere. Inside, on the surface, in the in-between part from the center to the circumference. Okay. Everywhere it is distributed uniformly. That is the meaning of a solid sphere. Okay. Which is uniformly charged. Like Earth has uniform mass. It's not a shell. It's not a hollow part. It's completely filled. So think of the charge to be distributed everywhere. Think of the charge to be distributed everywhere over here. Okay, so this is a solid uniform sphere. Now there are many things to this. Let me just create a duplicate over here. Charge is here, 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 everywhere. It is there everywhere around it. Okay, it's uniformly charged. Now we will take two different scenarios for this. We'll take two different scenarios for this. Again, case 1 and case 2. Once you are outside, once you are inside. So case 1, when you are basically outside, that means small r is more than capital R. And the second case, case 2, when you are basically inside, that means small r is less than capital R. Both these cases. When you're outside, actually the job is very simple. You take a Gaussian surface. You take a Gaussian surface, which is like this, spherical. So this is your Gaussian surface. This is your Gaussian surface, which is spherical, and it also has some radius. Let's say I will call it as small r. The radius of this particular thing is capital R, and the total charge on it is capital Q. Okay, I want to find what is the electric field at this particular point. So that is E. Also at that particular region, if I take a small area vector, that small area vector will be like this, parallel to the electric field. So this is a complete diagram to find the electric field outside a uniformly charged sphere. Outside a uniformly charged sphere. Now this is very simple to find. I'll tell you why. Because you will see it is just like the previous shell problem. If I use cyclic integral electric field area into cos 0, 0 because angle between field and area is 0, is equal to inside charge by epsilon naught. You will see the magnitude of the electric field at any distance is same. So it is a constant magnitude wise. So the magnitude can be shifted outside. Cos 0 is again 1. So I can just write it as electric field cyclic integral dA is equal to how much charge is there inside the blue part. It is the entire charge of the sphere, which is capital Q. So divide by epsilon naught. Now this part over here, the cyclic integral dA, this cyclic integral dA is the area of the Gaussian surface, which is nothing but 4 pi small r square, not capital R square. It is not the area of this part, it is the area of the Gaussian surface, because the areas are on the Gaussian surface. So our electric field will be as it is. This is Q by epsilon naught. Hence the electric field will be your 1 by 4 pi is there with epsilon naught. Q is there on the top and R square, which is the same as KQ divided by R square. This is just like a point charge. This is just like a point charge. So the entire charge behaves as if it is concentrated at the center. It behaves as if it is concentrated at the center. That is inside. Sorry, that was outside. Now let's go inside. If I'm inside, then the challenging part comes, because of Q inside. You will see how. Observe this carefully first. So let's say this is your capital R, the total charge is Q. Okay, I will choose a Gaussian surface inside to find the electric field inside, like this. This is your small r. So when I apply Gauss law, cyclic integral EdA cos 0 is equal to Q in divided by epsilon. Why is it cos 0? Simple explanation again. This will be your electric field anywhere. The area vector over here will again be parallel to the electric field. So this is dA. So this is basically your dA vector, which is your area vector. Cool. So they are parallel. That's why angle is 0, cos 0 is 1. Now, what you will see, interestingly, is that, observe carefully, guys. Electric field is constant, so it comes outside. Cos 0 is 1. Again, perfect. No issues there. So electric field is outside. Cyclic integral dA is the area of the Gaussian surface. Cyclic integral dA is the area of this Gaussian surface, which is the area of the sphere. Next step, it will become 4 pi small r square. That is something which I know. So this is E, just like before. The problem is not on the LHS. LHS wise it is same. The problem is on the RHS. Inside charge is not capital Q. Inside charge means only the charge present over here. Over here. How much charge is present there? That is the most important thing. So guys, to find that out, I'll tell you one very simple logic. Let me just probably take this part over here. Imagine I want to find how much charge is present only over here, only over here, only over here. This is small r. How much charge is present only in this particular part. If I use this concept of charge density, it becomes very simple. Charge density, which is charge per unit volume, charge per unit volume. I can say whatever is charge present here inside this blue part upon the volume of that sphere, which is 4 by 3 pi small r cube, is the charge density, is basically the charge density. Agree? The charge in this part upon the volume of this sphere is the charge density, but also the charge density is the total charge divided by the total volume. If this is capital R, then it is also 4 by 3 pi and capital R cube. Excellent. Now 4 by 3 pi, 4 by 3 pi cancels. 4 by 3 pi, 4 by 3 pi cancels. So what will I get? Q in divided by R cube is capital Q divided by capital R cube. So hence, what is the enclosed charge inside? Capital Q small r by capital R whole cube. That is what the charge present inside is. Use this over here. Use this over here. It is capital Q small r cube by capital R cube. Capital Q small r cube by capital R cube. Small r square, small r cube cancels. Hence, what will I be left with is electric field into 4 pi is equal to Q small r divided by R cube. Rearranging it further, electric field will be, I think that epsilon naught was also there. Yeah. Epsilon naught. So it will be 1 by 4 pi epsilon naught as it is, Q small r divided by capital R cube. So that extra small r is there. That is the only different thing inside. If you compare it with the shell, where inside a shell the field was 0, but for a solid sphere the field is not 0 inside. The field is not 0 inside. In fact, it is proportional to r. In fact, it is proportional to r, and that is what you will see. So in fact, I have shown that in the diagrammatical way here. If you are inside, it is kq by capital R cube into r, so it is proportional to r inside. But when you are outside, it is kq by r square. Kq by r square. Okay, that is the major difference in shell versus a solid sphere. And you can see that graphically it goes like this. When you're outside, it is inversely proportional to r square, but when you're inside, it is directly proportional to r. When you are inside, it is directly proportional to r. It is directly proportional to r. That's the thing. Is that clear, everyone? Okay. So inside directly proportional to r, the farther you are, it increases. When you are at the center, small r is 0. So electric field will be 0. And once you reach outside, it will again become inversely proportional to r square. That is why the graph is like this. That is why the graph is like this. Okay. Now, what about the electric potential? What about the electric potential? So electric field is done. What about the electric potential? Okay. Let's talk about potential. See, if you want to find the electric potential outside, it is actually very simple. When you want to find the electric potential outside, why is it simple? Because it behaves like a point charge. It behaves like a point charge. So the electric potential outside is the electric potential due to a point charge. It feels as if all the charge on the sphere is concentrated here. So the potential at this particular point will be just kq divided by the distance. As simple as that. Outside. As simple as that. Outside it is kq by small r. Is that absolutely understood? Very straightforward. Correct? Till this point, is it clear? Till this point, is it clear? Yep. Very good. The problem happens inside because there is field inside. Because there is field inside. Okay. Because there is field inside. That is why you will see the potential will not be constant. In fact, let's say you are at some distance smaller, okay, and you want to find the electric potential at this particular point. Okay, this is basically your R, this is capital Q. At that particular point, there will be some electric field which is E. There will be some electric field which is E. So, in order to find the potential at that point, understand, because electric field is not even constant. It is K Q small r divided by capital R cube. You will have to use integration to find the potential at that particular point. There is no other option. There is no other option. And how will you use integration? Observe this. In general, electric field is nothing but minus dV by dx. So minus dV is basically electric field into dx. So if I substitute electric field in terms of x, like it is kq divided by capital R cube into x, and that dx is there as it is. And on the left hand side, I still have that minus dV. I integrate both sides. So minus integration of dV. What will be my limits? I will come to that. I'll just put over here the constants outside. Kq by R cube are constants. Integration of x dx. Integration of x dx. What will be the limits? I will start from the origin or the center to basically R. That is one way. But the problem is I do not know the potential at the center. So it is always better to start from the surface, because on the surface, I know the electric potential. So you go from capital R to small r. That is the challenging part over here. That is the trick or the catch over here in this kind of derivation or problem. You do not go from the center, because when you put the limit here of potential, you cannot say 0. It is not 0 at the center. At the center, the potential is not 0, because the charges will give some potential. So you cannot start from 0. That is the catch. You start from the surface, and on the surface, I already know the potential formula, kq by capital R. So kq by capital R. So I can say potential on the surface will be KQ by capital R. You're just putting R is equal to R. That's all. You're just putting R is equal to R. So I know the potential on the surface on the left hand side. On the left hand side, I'm just going to put KQ divided by capital R, and at small r it is V. You integrate this to find that voltage. You integrate this to find that voltage, and that voltage comes out to be K, Q is there. Then you have 3R square minus R square, bracket complete, divided by 2R cube. 2R cube. This is the formula. KQ 3R square minus R square by 2R cube. In fact, if you find the potential at the center, potential at the center, it will be KQ. Center means uh, uh, one second. Here I had to just do one thing. R square minus 3R square will be the right way to do this. R square minus 3R square. Yep, now it is fine. Yeah, not 3R square minus R square. Okay, R square minus 3R square. Okay, so this is very important. So this will be R square minus 3 into 0 square, because small r will become 0 at the center. What will that small r become? That small r will become 0, divided by 2R cube. So 3 into 0, 0. So this will just become, sorry guys, my bad. Why did I do this mistake? So sorry, this is not the formula. What you get is 3 capital R square minus small r square. Sorry, it is 3 capital R square. So it is KQ 3 capital R square minus 0 square. So this will become K into Q into 3, and here you will have 2 and R cube and R square. So what will happen? One of the R will remain, other two R's will go off. So it will just become 3KQ divided by 2R. 3KQ divided by 2R, that is the potential at the center. Center means small r is 0. Small r is 0. So that small r is over here. That small r comes over here. Okay. So I'll just put it over here properly so that everybody is absolutely clear about it. You will have capital R square over here minus this small r square. Minus this small r square. Okay, very, very important. And this capital R cube is over here. Capital R cube is over here. This is the final formula. Yep. Cool, guys. Everybody fine till this point? Everybody fine till this point? So this is the only part where the formula is complicated. Otherwise, the formulas are very, very straightforward. Okay, and that too for potential of a solid sphere. Even the field of a solid sphere is simple. Field of a solid sphere is also simple. Potential outside is also simple. Shell is easy. Only the potential of the solid part, that too inside, is where that integration is involved. Otherwise, it is very, very straightforward question. Cool. Great. So remember this formula. I think I have put it on the next slide also. Yeah, potential inside versus potential outside. Okay, I think I would have put it over here in the graph form. Yeah, there it is. Inside it is a parabola, outside it is a hyperbola. I'll tell you why also it is a parabola. Observe this. This is a quadratic equation with a negative coefficient of the square term. That is why it is a parabola which is inverted. Okay, inside it is a quadratic equation. That is why it is a parabolic graph of potential versus distance. Why is it a hyperbola outside? Because if you see the formula for outside, see what it is. It is KQ by R, 1 by R proportional. So that is the reason why it is a hyperbola outside and it is a parabola inside. All these formulas are very, very important. Is that okay? Shall we go ahead? Yep. Shall we go ahead, my dear students? Sankuri, welcome. Hello. Where can I access to learn mathematics of 2 academic years? Meaning, Rakshana? It's there on the channel, old videos, if that's what you mean. if I'm a PCB computer science student, PCB computer science, why will you attend JEE? For the practice sake, Rakshana, you can give it. There is no harm, there is no limitation. Many biology students give JEE mains for practice. You just attempt physics and chemistry. You will leave mathematics part. Okay, cool. Yes, yes, TM players. Now it is fine, I hope. Great. Now, let's go to some questions. Let's see if you have some questions. Yes. Electric field in the region is radially outwards and has a magnitude E is kr. What is the charge contained in the sphere of radius A? Read this question again and see if it reminds you of something. Electric field is K times of R. This should remind you of electric field being proportional to R. And when is electric field proportional to R, my dear warriors? Inside a solid sphere. Exactly. If you remember, electric field inside a solid sphere, what is the formula? It is that constant, which is basically 1 by 4 pi epsilon naught, capital Q by capital R cube, and then you have small r. If you compare this with this, you will immediately realize that this K over here is just like this whole thing. So K is not that Coulomb's constant, some constant is Q by 4 pi epsilon naught R cube. Rearrange it, you will get Q is equal to 4 pi epsilon naught K capital R cube. 4 pi epsilon naught K capital R cube. But here R is nothing but the radius. So the radius is basically A. So it should be A cube. So I think the answer should be B. The answer should be B. Yes, the correct answer is B. Is that clear, my dear warriors? Very good. Very good. Rakshana, this has to be the biggest doubt of the century. I mean, what should I answer to this? You please tell me. I am a NEET aspirant, but want to choose engineering because I'm very weak in biology. What should I answer to this, Rakshana? It is like a JEE student is saying, Sir, I am a JEE aspirant, but I want to choose MBBS or I want to become a doctor because I'm very weak at mathematics. What were you doing from 10 to 11th? Who guided you? This is going to be very interesting. How did you leave mathematics like this? Can you change your subject right now in the college or school? Please do that. Change it to mathematics. Take a drop if needed. This is this has by the way happened with one of my student. I'll tell you, one of my student took PCMB, luckily at least, and she had enrolled for engineering, basically JEE course. 2 years she studied for JEE. After giving JEE means, she realized, I don't like engineering. I don't want to go into engineering. And then she decided, oh, wait a minute, I like biology more. I want to become a doctor. So she took a drop and then she prepared for PCB, prepared for NEET, and then cleared the NEET exam and now is pursuing a MBBS course. So it happens sometimes. Either you are misguided or you're not aware. But once you realize, change the path and go with what your heart and your mind says. But you should be convinced. That's the most important thing, right? Yo. Let's go ahead to the next question. It's going to come up on your screen. Okay, and then we are going to conductor and properties. Okay, great. So let me just give you a question before going to conductor and properties actually. Let's say we have a question like this. This is a sphere of radius r and charge q. This is another sphere of radius 3r and a charge of 2q. Some random things I have taken. And the question is to find the field and the potential at different regions. To find the field and the potential at different regions. Let's start one by one. Let's first go completely inside over here. Let's go completely inside over here, see what the field and the potential is. Then we will go into this particular region. We will go into um, this particular region over here. Very interesting region. You go to this particular region. Okay. And finally, we will go completely outside. Finally, we'll be going completely outside. Okay. In this particular region. In this particular region. Okay. Completely outside. So all the three regions, I want to know what the fields and the potentials are. What the fields and the potentials are. Okay. Let's do this. Let's do this. Starting off with completely inside. Starting off with completely inside. When you're completely inside, both the shells, each shell will have no contribution in the field. Think about it. So, when I try to find the field in that particular region, when I try to find the field in that first region, due to the inner shell versus the outer shell, both the contributions are zero. Hence, the field is just zero in this particular region number 1. Do you guys agree with it? Completely? Yep. Very good. Now, what about the potential? This is the interesting part. The potential in that region 1 is potential due to the inner shell plus potential due to the outer shell. If you talk about the inner shell, I am inside that shell having charge q. So the potential should be kq by the radius of the shell. No matter where I am, doesn't matter. Due to the shell of charge 2q, because again I am inside, it should be k, but the charge is 2q divided by the radius of that shell, which is basically 3r. So what will I get? What will I get? So kq by r is common. I have 1 plus 2 by 3. So 3 plus 2 is 5. So it will become 5 kq divided by 3r is the potential in that region number 1. This is the field which is 0. Potential is 5 kq by 3r everywhere. This point is clear? Everybody with me? Very good. This is a very good question, by the way, whatever I am doing right now. Okay, this could be a easily level 2 or level 3 question. Easily I can put it as level 2 question to level 3 question. Let's go to the region number 2. Let's go to region number 2. For region 2, you are outside the inner shell, but inside the outer shell. Interesting, right? So let's talk about the field first. The field will be field due to the inner shell. For the inner shell, I am outside. For the outer shell, I am inside. So for the inner shell, if I'm standing here, this is R. This charge which is there will be concentrated at the center. So the field will be kq divided by small r square. But for this outer shell, I am inside. Anywhere inside, the field contribution is 0. Hence, the answer is kq divided by r square in that region number 2. In that region number 2. Everybody with me? Very good. Now, what about the potential part? What about the potential part? Let's try to do this. Potential due to the inner shell, and I'm outside of it, plus potential due to the outer shell, where I'm inside of it. Due to the inner shell, this inner shell will behave like a point charge. So due to the point charge at this point, the potential will be kq divided by the distance. But due to the outer shell, because I'm inside, the potential everywhere will be constant. It will be kq by the radius of the shell. So k into charge by the radius of the shell, which is basically 3r. Hence, that is the potential formula. This is small r, this is capital R. Unlike previously, where both were capital R's. Is that absolutely clear, my dear warriors? Very good. Now let's go to the outermost region, which I call it as region number 3. Okay. For the outermost region number 3, the electric field due to the inner plus the outer shells, I am outside for both the shells. When I am here, think about it. When I am here, this is R. I am outside for both the shells. So guys, both of them will behave like point charges. So it will be kq by r square plus k 2q by r square. So it will become 2 plus 1 is 3. So 3kq divided by r square. That is the field in that region 3 outside. In that region 3 outside. What about the potential? Well, for the potential due to inner shell, potential due to outer shell, I am outside both of them. I'm outside both of them. So when I'm here, both these shells will behave like point charges. So it will be kq divided by r plus k 2q divided by small r. So 2 plus 1 is 3. So 3kq divided by small r is the potential in region number 3. In region number 3. That's it. That's how you solve this problem. So I think this problem is a very good problem to understand and explain how the potentials change, fields change inside, outside, different layers of shell. Different layers of shell. Is that okay? Shall we go ahead? Loved this question. Everybody, concept is clear. Can we now go to properties of conductors? Some important properties of conductors, earthing, connecting conductors, field properties, etc., etc. Yep. Ready, guys, for the final, final part of this particular chapter? Okay. What are the some of the important properties of a conductor? One of the first important properties. One of the first important properties. Number one. You give me a conductor like this, solid conductor, okay, or a conductor with some cavity in it, like this, or multiple cavities in it, or multiple cavities in it, something like this. These are basically conductors with cavities, with cavities, or this is just a pure solid conductor without any cavity. If you charge any of these, if you charge any of these conductors, you will see the charge is always on the outermost surface, because the charges don't like each other. If I charge it positively, all the charges will go on the surface. They don't like each other. The best possible scenario will be they are on the surface as away as possible. It's like saying, you are in a class of 60 to 100 students and everybody dislikes everyone. Just imagine a classroom like that. It never happens, but hypothetical classroom. Everybody dislikes everyone. Everybody will stay away from each other. What will they do? They will all stand on the periphery. They don't like to be with each other. They will all repel each other. So you will see that the charges are always on the surface. This is one of the most important thing. Not on the surface of the cavity, on the outermost surface. Even if it is negative charge, doesn't matter. Even if it is negative charge, doesn't matter. It is always on the surface, not on the surface of the cavity. Is this clear? So this is the first important thing which I will mention it. The charges are on the outer surface. On the outer surface. This is the first important property which you are seeing. Let's go to the next property, guys. Let's go to the next property now. Property number two. Property number two of conductors. Everything, whatever you are seeing, is just pure properties of conductors and conductors alone. When you show the field lines for a conductor, let's say this is a conductor. The charges are always going to be on the surface. you will see that the electric field lines, always are going to be outside, probably something like this. And not just that, you will see that they are always perpendicular to the surface at every given instance. They're always going to be perpendicular to the surface no matter where they are. Always perpendicular outside. And once they go real far away, it need not be perpendicular. It can take its own due course, own due path. Whereas inside, the field will be a big fat zero. Inside, the electric field will be zero. And you will see outside, electric field on the surface outside is perpendicular to the surface of the conductor, very very important thing, not just that, the electric field on the surface of the conductor is given by sigma by epsilon. There is no 2 over here. Compare it with this formula for a sheet. Where the sheet went. Right over here. For a sheet, sigma by 2 epsilon. Here, the field is there right side, left side, both places. The field is there right side, left side. So it gets divided into 2. So that's why sigma by 2 epsilon. That's why sigma by 2, because it is getting divided by 2. Whereas in this scenario, in case of a conductor, pure conductor, the field is not going inside and outside. It is only going in one direction, outside. So it is sigma by epsilon. A very important formula. A very, very important formula. Is this clear, everyone, till this point? Very nice. Very nice. Okay, great. Electric field inside is zero. One more thing that you will notice, because the field inside is zero, what can you say about the potential which is there inside? It will be constant. So all the points inside the conductor are equipotential. So all points inside are equipotential. They are equipotential and have no field. At all. Only it's outside which is having some field. Correct. Very good. Moving on to the next property of the conductor. This was the second property. We saw the first property. Now let's go to the third property. Third property of a conductor. Let's say you take a conductor of any random shape like this. You will see when the charges get distributed on the surface, they are not evenly distributed. What you will notice is that wherever the surface is curved, in fact more curved, the charges will be present in higher concentration. And as you go to a blunt surface, the distribution is little bit less. That is how it looks like. As you go to the sharper surface, more curved surface, the distribution is more. As you go more towards the blunt surface, you will see the distribution is slightly less. That's how it works. So in fact, even the field will be very, very strong over here. The field will also be very, very strong over here, versus over here, the field strength will be very, very weak. So this will be a weaker electric field versus a strong electric field Here, higher charge concentration, because you can see the radius is very, very small versus a large radius. So this is a sharp edge versus a blunt edge. In fact, this is also the reason why you should be aware when you're going outside, especially the thunderstorms are occurring, lightning is occurring, and your hair begins to stand. Imagine there is a pandu like this. This pandu has gone outside, and then the hair of the pandu begins to stand like this. There were photographs which were clicked during rainy season of some person, and the hair began to stand. So the person got very fascinated. Oh, my hair is standing. Wow, so cool. How is it standing like this? One strand also. Imagine if you are a girl with long hair, then the hair will stand even like this. So the person got fascinated. But actually, it's a very dangerous sign. The sign is run. Run like crazy fellow. Don't even wait for 1 second. Reason is your hair is also like a partial conductor. The reason why it is standing is because the charges have got accumulated. The charges have got accumulated on the tips of your hair, which is very, very sharp. So there are strong electric field lines which are coming out of it. Strong field which is coming out of it. And where is that strong field going? That strong field is going to the clouds. And there is a conducting path. And there is a conducting path from the clouds to your hair, guys. This is your pandu over here. Yep. So there is a nice conducting path from your hair to the clouds. So if lightning comes, it will take that path of that strong electric field and it will enter your head and it will kill you. So that is the reason why you should run. That is the reason why you should run. Not just that, you will see on tall buildings, they put a lightning conductor which is very sharp. Why? Because it should not damage the building or anything. So because the lightning conductor is sharp, you will see strong electric fields will be concentrated over there at the lightning conductor. So if lightning occurs also, it will pass through that lightning conductor, which is indirectly connected to the earth finally. So all the charges safely enter into the earth. That is what happens. So this is the concept of sharp edge versus blunt edge. Weaker field at the blunt edge where the charges are also less. At a sharp edge, strong field where the charges are also more. In fact, you can also say sigma is inversely proportional to the radius of curvature. Very, very important thing. So therefore, sigma 1 by sigma 2 is R2 by R1, and sigma 1 by sigma 2 is also E1 by E2, electric field at those locations. So this is the formula that you need to remember. Sigma is inversely proportional to the radius of curvature at those locations. Clear? Everyone with me? Okay. Great. Formula revision, I have already done the Sri V. Just go to the YouTube channel, our YouTube channel, okay, and just search over here formulas. Just search over here formula physics. Just search over here formula physics. You will see all formula revision sessions are there. So just use any of these sessions. In fact, use the latest one only. Use the latest one, which was here. Complete physics formula revision. This was 1 year back. This year also I have done it. Yeah, this one. 5 months ago. You can use this. Okay? Fair enough. All chapter formulas are done. Great. Next important property. Okay. Next important property. If you have a conductor, let's say over here, and you bring a charge from outside, like this. This is an actual charge or charged body from outside. Then what happens is that charged body will attract or repel the electrons depending on the charge. If it is a positive charge, it will attract the electrons. If it is a negative charge, it will repel the electrons. So because it is positive charge, it will attract the electrons. So this conductor is made of free electrons and the nucleus is made is positive in nature. So these free electrons are free to move. So we will see the electrons will get attracted and it will move towards this side where the positive charge is kept. Obviously, because the electrons have left the individual atoms. It's like, there were Pandus and Champas in a relationship, and this is a very, very hot Pandu who came. A very, very hot Pandu who came. So these Champas left those Pandus and now are getting very close. It's like a superstar, some celebrity has come. Okay, so all those boyfriend, girlfriends, their relationships got broken. All these girls have come to meet this superstar. They have come close, but they can't come and jump onto the superstar because there is a air gap in between, there is vacuum in between, non-conducting path. It is like a stage is there, this is the playground. So these are the Pandus who got left out. These are the Pandus who got left out. So Pandus definitely will take revenge in the next case. And what will happen is, let's say another conductor, some favorite heroine came. Who is your favorite heroine these days? I don't know. Okay, some favorite heroine came over here. Let's take some charge like this, negative. So this heroine came, all the Pandus left their Champas, they arrived here, but they can't jump onto this heroine because there is a non-conducting path over here. And who got left out? This time it was Champas. So all the Champas are right over here. All the Champas are right over here. Got it, my dear warriors? Yep, correct. Very good. Now, these charges which are shown on this side and this side, they are called as induced charge. So, they are basically induced charge. So, this is minus Q induced. So, this will be positive induced charge. Positive induced charge. Here also, plus Q induced, and this will be minus Q induced. So, charges get induced. So, charges are induced. So I would say charges are induced. Charges are induced on the surface. Charges are induced on the surface. This is what you will see. Not just that, you will also see one very interesting thing. Because the negative is closer to the positive than the positive to the positive, so there will be a stronger attraction. The attraction will be a stronger attraction than the repulsion between the charges which are far away. So this will be a weaker repulsion, because of which the net force on the conductor will be this way. So this is the direction of the net force on the conductor. So the conductor gets attracted towards the charge. So the conductor is attracted to the charge. The conductor is attracted to the charge. Very, very important thing. Not just that, you will see that there will be electric field lines. There will be also electric field lines. I'll probably show it on the next slide. That will be better. Electric field lines which will go like this: positive to negative, 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 positive. They can't go to positive. They can't go to positive. You will see probably something like this, maybe. Yeah. This is the kind of electric field lines which you will probably see. Okay, from the positive to the negative charge. But still, even in this case, you will see inside the electric field will be zero. So the distribution of the charges happens in such a way that no electric field line cuts through the conductor. Still the field inside will be zero. Field inside is going to be a zero. Even if, imagine there was a cavity over here. Imagine there was a cavity over here, and this charge was there outside. This charge was there outside. There is no way you would know if the charge is there outside. So this is a conductor with cavity. So this is a conductor with cavity. Anyways, the field was zero. Here also the field will be zero everywhere. There was no way you would know what the charge was there. Was there any charge at all? Where was it? Nothing. You will see that the field lines will go like this, like this, like this, like this, like this. Probably you will have some field lines, sorry, field lines like this, like this, like this, like this, like this, probably like this, like this, like this, like this, okay, like this. So you'll have these field lines outside, but inside there is no way you would know that, there was a charge outside. This is called a shielding effect. So if you want to go out of coverage, because your mobile phone works on electromagnetic waves, and electromagnetic waves means electric field and magnetic field, you can get rid of the electric field in a very simple way. You take this mobile and put it in a container, not a wooden box. So you might think, I will put the phone inside the drawer, it will show unreachable. No, you take a metallic box, a very good conductor like a copper container. Don't even use aluminum. Aluminum is good, but not the best conductor. Take a copper container, or silver will be very costly. Gold will be even more costly. That's why I said copper. And put it inside the copper vessel, and you will see that the mobile phone will show out of coverage. Why? Because electromagnetic field lines cannot travel inside. So this is also called as the shielding effect. What is it called? Shielding effect, because you are shielding the outside field inside. Just like how the ozone layer protects us from the harmful UV layers, same way this conductor is protecting us from the electric field when you are inside. So that is why it is called as the shield. Is that clear? Sir, did I come late to the class? No, Shanmuga. Who said you are come late to the class? You are very early for the next class. Okay. So moving on, so that was your fourth property, guys, about induced charges when you are placing another charge body outside. The next property, let's go to it. The next property, I think then we have earthing and connecting later on. Okay. The next property, the fifth one, is when you are placing a charge inside the conductor, which has some cavity. Okay, this is a conductor with cavity. Okay, this is a, oops, why is it looking so bad? Okay, this is a conductor with cavity. And let's say you take a charge, right? Okay, my God, better to draw it. Okay, so this is basically a conductor with cavity, a conductor with cavity and charge inside, and charge basically inside. So just imagine, you are placing a charge over here. What will happen is this charge will immediately attract or repel, depending on the sign, the charges on the conductor, because this is a positively charged uh, uh, point. So it will immediately attract the electrons. So this is like a center stage. Some hero has come or heroine has come. All the champas or the pandus will leave their respective places. So here electrons have accumulated on the periphery. Who have they left? Their positive charges. So the positive charge will be on the outer surface. The positive charge basically will be on the outer surface. So this is how it will look like. This is how it will look like. Is it not interesting, guys? So cool. It has created induced charges. So this is positive induced charge, and this is basically negative induced charge. And now the best part is the positive charge only depends, distribution of the positive charge only depends on the shape of the conductor and the size of the conductor on the surface. It doesn't matter where this charge is. Even if I move this charge here, then these negative charges will reallocate themselves, redistribute themselves, but the positive charge will still stay intact. So very, very important, the charges on the surface of the cavity, on the surface of the cavity distribute depending on distribute depending on the placement depending on the placement of the charge of the charge. This is one of the important things. The charges on the surface of the cavity depends on where you place this positive charge. If you bring this here, then you will see there will be more negative charges on this side as compared to on this side, because this positive is close to this surface, so more people will be accumulated over here, more electrons will be accumulated over here. Whereas if you talk about the outer surface, the distribution of outer charges of outer charges is of outer charges is independent of the inner charge which I have placed, and only depends on the outer surface, geometry, meaning their shape and their size. How this shape and size is. If this is sharp, more charges here. If this is blunt, less charges there. Accordingly, it will get redistributed or reallocated. That is the major difference. Cool. So these are major properties. Now we will go to basically another few properties which are there. That is connecting it to the earth and connecting two conductors together. These are last two properties. These are the last two properties. So we have done till 5 properties here. Let's go to the 6th and the 7th property. This is your 6th property, earthing a conductor. Meaning, if you take a conductor, and you take a wire, and insert it below the earth's surface. This is your earth's surface. You insert it below the earth's surface and leave it over there. You will see if there were some charges on it, they will rearrange, they will go somewhere, do something till these two will come to the same potential. In fact, the potential of the earth is 0, means that this conductor will come to 0 potential. So keep this in mind. Earth's surface, basically the earth, is at 0 volts potential. So when you connect this wire inside the earth, usually the symbol for earthing is this. This process is called as earthing. You will see that this conductor, the potential of this particular conductor will be 0 volts. So anything connected to the earth will come to 0 volts. And this is a very important thing in many places as an application. Say for example, we have a careless pandu. Who do we have? Careless pandu. And careless pandu happens to, this careless pandu is touching some electrical appliance like a microwave oven. Now, what is the problem with that microwave oven? I'll tell you. There is some loose wire in that microwave oven. So what is happening is, that in that microwave which is connected to the power, there is current which is coming in, current which is also going out, but that current is also going to the body of the microwave. So imagine this careless pandu touches the microwave oven's body. What will happen? This current will find a path to go via the pandu and inside the earth. So pandu this careless Pandu, all right, he will get a nice electric shock. If he was a careful Pandu, he would be wearing insulating shoes or rubber material, or he's standing on a rubber mat or a non-conducting mat. Then the current does not have a path to go inside the earth. So then the Pandu is safe. Then the Pandu is safe. Is that right? Clear? So now, because Pandu is not wearing shoes, the current will go inside Pandu and Pandu will get shocked. So careless Pandu is shocked. Careless Pandu is basically shocked. Now, Pandus are careless. We have to deal with it. So we have to take the precaution. Who? The person who made the microwave. So what happens in the next scenario is, again you have that careless Pandu who is touching that microwave oven which has a loose wire. But this time what you do is, apart from the two wires which are connected to the electric socket, you have one more wire. You have one more wire which is called as the ground wire, and that is connected indirectly to the earth. Indirectly to the earth. And this ground wire is connected to the body of the microwave, the metallic parts of the microwave. So when the current leaks, the current has two paths. Path 1 to go via Pandu. Path 1 to go via Pandu. Path 2, because it is connected to the body of the conductor, via the earthing wire. This is the path number 2. Now the current will think, how do I go? Should I go via Pandu? Should I go via the earthing wire? Should I go via Pandu? Should I go via the earthing wire? Then it knows Pandu has a higher resistance. This earthing wire has very, very low resistance. Human body is not a good conductor, it is a decent conductor. We have lots of kilo ohms of resistance. So the current will decide to take path 2 and not path 1. So even if the Pandu is careless, the current will go into the ground. The current will go into the ground. Yes. Subhash, I'm from ITT. I followed Vedantu JEE English for preparation and Capto was my inspiration. Thank you so much, Subhash. Thank you so much. Glad. IIT Madras. Okay. That's what I was wondering. ITT. Okay. Glad. Oh my God, Subhash, you're in IIT Madras. So cool, yeah. So cool. Someday, probably you should come down to Bangalore office and give a talk on this channel. Students will be so motivated. And I'm so glad that you guys keep coming and keep inspiring all the juniors. That's a very nice tradition to follow. Thank you so much. Okay, so this is a path. That is why you have the grounding wire. So you'll see most of the switches these days, they have, not the double plug, you will have the three plug. Yeah, the three plug. That big thing on the top is that earthing part. Okay, so that is the concept of earthing. The last part that we have is connecting of conductors. Very, very important. If you have two conductors, and you take a wire and join these two conductors. So conductors are connected. Then what happens is, you will see that current will flow. First important thing, the current flows from the conductor with high potential to the conductor with low potential, and eventually the current stops. When does the current stops? When the current stops, when both have same potential. That's when you will say equilibrium is achieved. And they behave like, now they don't behave like two separate conductors. Once equipotential surface is achieved, they behave like one big conductor. They act like a single bigger conductor. That is what happens when you connect two conductors with a wire. It's like two buckets, one which has more water, one which has less water. The bucket which has more water, the water flows from the bucket to the lower bucket, and the level of the water will become equal. Here the water level corresponds to voltage. So the voltages become equal. That's what happens. That's what happens. Okay. I hope this is very, very clear. Excellent. Let's solve some questions. Two charge conducting spheres of radius A and B are connected to each other by a conducting wire. The ratio of the charges of the two spheres is respectively. This was asked in JEE Mains 2024, this year alone. So how do we solve this? Two conductors, charge spheres of radius A and radius B, they were connected by a wire. The moment you connect it by a wire, they behave like one single conductor. And we know one thing, the charge distribution happens based on the radius of curvature. The one which has more radius has less charge, one which has less radius has more charge. So using the concept, charge density is inversely proportional to the radius. The ratio of the charges of the two spheres, okay, is how much? So sigma A by sigma B is radius inversely proportional. Sigma is charge by area. So charge on A by the area, which is 4 pi A square, upon charge on B by radius, which area, which is 4 pi B square, is equal to B by A. So QA by QB, 4 pi cancels, B square goes on the top. B square goes on the top, A square stays here. So B by A. A cancels. So I am left with QA by QB. Uh, into B by A is equal to 1. So QA divided by QB is equal to A divided by B. So A divided by B is option number C. A divided by B is option number C. Is that clear, my dear students? Yep. So the charge density is inversely proportional to the radius is a property of the conductor which has been used in solving this particular question. Clear? Amazing, amazing, amazing. Moving on. Yeah, this was the question. I think that's it. That's the last question for this particular lecture. So we have completed the entire theory. We have solved many problems of this chapter. Properties of conductor, very low weightage from mains perspective. JEE Advanced, yes, maybe some questions might come. We'll solve obviously problems on one particular day from all the chapters together. We'll have problem solving sessions, but for now, let's complete the syllabus. And I hope you learned all the theorems, learned all the properties, learned how the formulas are used and how they are derived, everything in detail in this particular road series. So all the lines, do not forget to leave a comment which chapter you want next and how you enjoyed this class if you're watching it after a long time. Cool. Thank you so much, guys. And the PDF will be available in the Jungle Book. Okay. Take care. Bye bye. Take care. Hasta la vista.